From far away, a spiral galaxy looks almost entirely complete. Its bright center glows like a crowded island, while curved arms sweep outward through the dark. Billions of stars mark its shape. Clouds of gas catch their light. From this distance, everything that matters seems to be visible. The brighter regions appear dense and heavy. The faint edges appear thin and nearly empty. Beyond them lies what looks like ordinary darkness, a silent border where the galaxy seems to end. That picture feels natural, because light is how we usually learn where things are. A star announces itself by shining. A cloud becomes visible when it absorbs or reflects radiation. Even objects too distant for our eyes can be found when telescopes collect the light they release. The image may be faint, blurred, or incomplete, but it still encourages a simple belief. Where the light ends, most of the matter should end as well. Yet the galaxy does not move as though that belief were true. Stars and gas orbit the galactic center. Their motion is controlled by gravity, and gravity depends on the mass inside their paths. If nearly all of a galaxy's mass were concentrated in its bright inner regions, objects farther from the center should orbit more slowly. The same basic pattern appears in a solar system. A nearby planet moves rapidly around its star, while a distant planet travels more slowly because most of the system's mass remains concentrated at the center. A galaxy is more complicated than a solar system, but the expectation is still clear. Once an orbit reaches far beyond most of the visible stars, the speed should begin to fall. There should be less additional matter inside each wider path, so the outer regions should reveal the fading influence of the bright galaxy behind them. Instead, the measured speeds remain unexpectedly high. Far from the glowing center, where the visible material has become sparse, stars and clouds of gas continue moving with enough speed that they should not remain bound if the matter we can see were all that existed. The galaxy behaves as if its gravitational reach extends far beyond its luminous outline. The darkness outside the bright disk may look empty, but the motion passing through it tells a different story. Something there appears to be pulling. This does not mean astronomers have taken a photograph of a hidden substance. It does not mean a telescope has found a dark cloud waiting behind the stars. The evidence begins with a mismatch between two maps. One map is drawn by light and shows where visible matter appears to be. The other is drawn by motion and shows how much gravity is acting. When those maps are compared, the gravitational galaxy is larger and heavier than the luminous galaxy. The difference is not small. Across the universe as a whole, the leading cosmological model indicates that dark matter outweighs ordinary matter by roughly 5-to-1. That ratio describes a cosmic average, not the contents of every individual place. Earth, a star, or a glowing gas cloud is made mostly of ordinary matter. But when the universe is considered on its largest scales, the matter that forms planets, oceans, bodies, and every familiar object appears to be the minority component. Most matter does not shine. That statement can sound frightening, but not because dark matter is known to be hostile. There is no scientific evidence that it is watching us, approaching us, or waiting to cause some disaster. Its name does not describe an intention. The unsettling part is quieter. Everything humans have ever seen has reached us through some interaction with light, yet the larger share of matter appears to exist outside that familiar channel. It shapes the visible universe, while remaining absent from the pictures through which we first learned the universe was there. The darkness is therefore not terrifying in the sense of a threat. It is unsettling because it exposes a limit. Our eyes reveal only what can exchange light with them. Our telescopes, however powerful, also depend on radiation arriving at their instruments. If a form of matter does not emit, reflect, or noticeably absorb that radiation, then making a telescope larger will not automatically bring it into view. The universe may contain immense physical structures that no ordinary image can display directly. Still, invisibility is not the same as absence. A thing can be known through what it changes. Wind is traced by moving leaves. An unseen planet can be inferred from the repeated motion of a visible star. In a similar way, the outer parts of a galaxy act like markers carried along by a gravitational field. Their paths suggest that the bright disk is sitting inside something much larger, even if that larger structure contributes no visible glow of its own. This changes the meaning of the galactic image. The spiral is not the full object. It may be only the luminous part of a much wider system whose boundaries are traced by gravity instead of light. The stars are no longer simply decorations inside an empty night. They become test particles, each orbit carrying information about mass that cannot be photographed. The darker the outskirts become, the more important their motion may be, because there is less visible material available to explain it. What first appeared to be the end of the galaxy becomes the place where the discrepancy is hardest to ignore. The image shows only the part capable of introducing itself through light. The rest must be approached indirectly, through patterns that remain after every visible source has been counted, and through effects that cannot be dismissed merely because their cause does not shine. But this first clue does not settle the case. Motion must be interpreted through a theory of gravity. If the outer stars are moving faster than expected, perhaps there is unseen mass pulling them, or perhaps the rules used to predict their motion do not work in exactly the same way across a galaxy. The observation is real, but more than one explanation can be placed behind it. A surprising orbit can reveal that a problem exists without telling us which solution nature has chosen. That distinction controls everything that follows. The investigation is not simply a search for a mysterious particle. It is an attempt to understand how scientists can establish the presence of something that gives them no ordinary image, how several independent kinds of evidence can be compared, and how confidence can grow even while the underlying identity remains unknown. So the central question is more precise than asking why space looks dark. How can we know that most matter is present when it cannot be seen, and what does its continued invisibility reveal, or fail to reveal, about reality? The fast-moving edges of galaxies offer a powerful beginning. They show that visible matter and gravitational influence do not line up in the way we expect, but they remain only a beginning. Before the hidden mass can be weighed, mapped, or named, we must decide what invisible actually means, what counts as detection, and whether gravity can reveal a reality that light never shows. To decide whether gravity can reveal a reality that light never shows, we first need to be careful with one familiar word. Invisible can mean several different things. An object may be too faint, too distant, hidden behind something brighter, or beyond the range of human eyes. None of those meanings is quite strong enough for dark matter. When scientists describe dark matter as invisible, they are not simply saying that it is difficult to photograph. They mean that it has not been observed emitting, reflecting, absorbing, or scattering light in the ordinary ways that make matter visible. Every normal image begins with photons. Photons are the particles of electromagnetic radiation, which includes visible light, radio waves, infrared, ultraviolet, X-rays, and gamma rays. A warm cloud can reveal itself through infrared radiation. Cold hydrogen can be mapped through radio signals. Hot gas can shine in X-rays. Dust may appear as a dark shape because it absorbs light coming from behind it. Different instruments collect different parts of this broad electromagnetic spectrum, allowing astronomers to see far more than human eyes alone could ever detect. But all these methods depend on some exchange of electromagnetic radiation. Something must produce photons, change them, block them, or redirect them strongly enough to leave a measurable signal. If a form of matter does none of those things at a detectable level, then switching from an optical telescope to a radio or X-ray telescope does not solve the basic problem. The instrument is still waiting for an electromagnetic message that never clearly arrives. This is the specific sense in which dark matter is dark. No meaningful electromagnetic interaction has been securely detected. It does not build a conventional image of itself through light. That statement must be phrased with care. Science has not proved that every possible interaction is exactly zero. Extremely weak effects may remain below present sensitivity. The accurate claim is that gravity is the interaction established through observation, while any other interaction remains unconfirmed. Scientific language separates three ideas that everyday speech often blends together. The first is that a signal has not been detected. This describes the present result of a particular observation or experiment. The second is that a possible signal has been constrained. This means the search was sensitive enough to show that any effect of the tested kind must be weaker or rarer than a stated limit. The third is that an interaction is impossible. That final claim is far stronger and usually requires much more than repeated silence from instruments. A detector can listen within only a defined range, using assumptions about what the signal should look like. If nothing appears, the result closes part of the search space. It does not automatically close every door. This distinction will become important when physical candidates are eventually tested. For the present argument, it establishes a rule. Absence of an electromagnetic signal supports the description of darkness, but it does not grant unlimited knowledge about why the signal is absent. Dark matter could interact at a level below current reach, through a channel not yet recognized, or only under conditions our instruments have not examined. None of these possibilities is established. They simply explain why careful wording protects the evidence from becoming a claim larger than the measurement itself. That difference matters because invisible is often confused with undetectable. They are not the same. A physical cause can leave no direct image and still produce measurable consequences. We do not need to see every object in the same way before we can learn that it exists. What matters is whether its effects form a reliable pattern, whether competing explanations can be tested, and whether independent measurements lead toward the same conclusion. Consider a black hole. Its central region does not send ordinary light back to us, yet matter around it can become bright. Nearby stars can follow revealing orbits, and passing light can be distorted. Or consider neutrinos, which can cross enormous amounts of ordinary matter with very little interaction. They are extraordinarily difficult to catch, but they are not beyond measurement. These comparisons do not mean dark matter is a black hole or a neutrino. They show only that direct visibility is not the boundary between physical knowledge and complete ignorance. The first level of knowledge is direct observation or measurement. A detector records a signal, a position, an energy, a wavelength, a speed, or a change in brightness. Even here, the phrase direct observation can be misleading if it suggests unfiltered contact with reality. Instruments turn physical events into data, and those data must be calibrated and interpreted. Still, the measurement itself is the closest layer to what happened. The second level is strong scientific inference. We observe one effect and identify the cause that best explains a wider pattern. The cause may not be visible in an image, but it repeatedly predicts what visible objects will do. When many measurements agree, when alternative causes fail important tests, and when the explanation works across different systems, the inference becomes powerful. Much of the case for dark matter belongs at this level. Its gravitational influence is inferred from the behavior of things that can be measured. The third level is a model-dependent conclusion. A model connects measurements through a set of assumptions and physical laws. It may describe how mass is distributed, how the universe changes, or how a signal should appear inside a detector. Models are not guesses made without discipline. They can be precise, predictive, and exposed to failure. But their conclusions must remain attached to their assumptions. A number derived within a successful cosmological model is not identical to a substance captured in a laboratory. The fourth level is speculation about identity. Once observations indicate an unseen gravitational component, physicists can ask what kind of particle, field, compact object, or deeper phenomenon could produce it. Those possibilities may be mathematically serious and scientifically testable. They may even solve other problems at the same time, yet a well-motivated candidate is still not a discovery. The evidence for an unexplained effect cannot automatically be transferred to whichever proposed identity is most elegant or popular. The final level is philosophical reflection. The fact that most matter may lie outside direct electromagnetic vision can change how we think about human perception and knowledge. That reflection may be meaningful, but it is not another measurement. It cannot be placed in the same evidence category as an orbit, a lensing pattern, or a detector result. Keeping these layers separate does not weaken the mystery. It prevents the emotional meaning of the subject from being mistaken for a physical claim. Gravity allows these layers to connect because gravity does not require an object to shine. A planet pulls on its star, whether either one is being watched. A mass changes the motion of nearby matter regardless of its color. In the modern description of gravity, mass and energy also shape space-time, changing the paths followed by objects and by light itself. Those changed paths can carry information about a source that contributes no light of its own. This gives astronomers two broad ways to trace invisible gravity. They can study motion, asking what distribution of mass is needed to produce the measured paths and speeds of visible objects. They can also study how light from a more distant source is bent on its journey toward us. That bending is called gravitational lensing. Under the right conditions, it can stretch, magnify, or subtly reshape the appearance of background objects. By measuring those changes, astronomers can reconstruct where gravitational influence is concentrated, even when the source of that influence is not luminous. For now, the important point is not how a lensing map is built. That requires its own careful explanation. The important point is that light can reveal dark matter without being emitted by dark matter. The photons may come from a galaxy far behind the mass being studied. Dark matter contributes no picture of itself, but its gravity changes the route those photons take. It becomes legible through its effect on a message sent by something else. This is indirect evidence, but indirect does not mean weak. A fingerprint is indirect evidence of a person who is no longer in the room. The motion of a visible star can reveal a companion hidden in its glare. The strength of any inference depends on the quality of the pattern and the ability to rule out alternatives, not on whether the cause poses for a photograph. In astronomy, distance ensures that much of what we know comes through consequences rather than physical samples. At the same time, Indirect evidence creates responsibilities. Scientists must ask whether visible matter has been counted correctly. They must test whether a system is stable enough for the chosen calculation. They must examine whether the law of gravity is being applied in a regime where it has been tested. They must compare different methods whose weaknesses are not identical. If several routes point toward the same unseen mass, confidence grows. If they disagree, the disagreement becomes evidence that an assumption or measurement may be wrong. This is why one surprising galaxy cannot carry the entire case. Its fast outer material establishes a contradiction, but that contradiction may have several explanations. Perhaps faint ordinary matter was missed. Perhaps the system is not behaving as simply as assumed. Perhaps gravity changes across vast distances or under extremely weak acceleration. Or perhaps a new component supplies the missing pull. The investigation becomes convincing only when these possibilities face evidence from different places, scales, and periods of cosmic history. Dark matter is therefore electromagnetically invisible but gravitationally legible. We do not receive a normal image from it, yet we can measure patterns associated with its pull. That is already a meaningful answer to the question of detection. It tells us that human knowledge is not restricted to substances that announce themselves with light. But it is not an answer to the deeper question of identity. Knowing that something bends paths without shining does not tell us what that something is. Several possible causes can share the same broad gravitational signature. To move beyond a single mismatch, we need to see whether the missing pull appeared again, whether better measurements preserved it, and whether it became a stable astronomical problem rather than an isolated surprise. That trail begins before modern detectors and precision maps, when astronomers first tried to weigh immense gatherings of galaxies. Their measurements were uncertain, their tools were limited, and their first estimates were far from final. Yet inside those early observations was a discrepancy that would refuse to disappear. The visible members of a cosmic system did not seem heavy enough to explain how the whole system moved under its gravity. The first missing mass did not appear at the edge of a single spiral galaxy. It emerged on a larger scale, inside a gathering so vast that entire galaxies became the moving points used to measure it. The Coma cluster is a great collection of galaxies held together by gravity. Seen in an image, its members look scattered across the same region of sky. But an image alone cannot show whether they form a stable physical system, how quickly they move through that system, or how much total mass is needed to keep them from escaping. To answer those questions, astronomers had to treat the cluster as more than a picture. They had to turn it into a scale. In the early 20th century, light from distant galaxies could already reveal motion along our line of sight. Features in a galaxy's spectrum shift when that galaxy moves toward or away from us. By measuring those shifts for several members of a cluster, astronomers could estimate how quickly the galaxies were traveling relative to one another. Their speeds were not merely descriptive. They carried information about the gravitational field through which the galaxies moved. This was the setting in which Fritz Zwicky studied the Coma cluster in the 1930s. His reasoning followed a basic physical demand. If the galaxies belong to one long-lived, gravitationally bound cluster, then the cluster needed enough mass to prevent their measured motions from carrying them apart. Fast members required a stronger collective pull. A stronger pull required more mass. The method drew on what is called the virial theorem. Its mathematical form was more precise than any simple analogy, but its central idea can be expressed plainly. In a settled gravitational system, motion and binding are related. The average energy in the movement of its members must be balanced by the gravitational structure holding the system together. Measure how widely the members are spread, measure how quickly they move, and it becomes possible to estimate the mass needed to bind them. Imagine watching a swarm of objects circling inside an invisible enclosure. If they drift slowly, a modest inward pull may be enough to contain them. If they race in different directions, the enclosure must exert a much stronger influence or the swarm will disperse. A galaxy cluster has no physical wall. Gravity provides the only enclosure. The faster its galaxies move, the more gravitating mass the cluster must contain if it is to remain intact. Zwicky compared the mass implied by the galaxy's motion with the mass suggested by their visible light. The two estimates did not agree. The luminous galaxies appeared to provide far too little gravity to account for the speeds he had measured. Either the cluster was not the stable system assumed by the calculation, the observations or mass estimates were badly incomplete, or much of the required mass produced little or no visible light. This was an early version of the problem now associated with dark matter. But it was not a modern dark matter detection, arriving decades ahead of every uncertainty. Zwicky's original numbers were built from the limited observations and astronomical knowledge available at the time. The scale of his discrepancy should not be lifted from that historical setting and repeated as though every part of it retained modern precision. What lasted was not one exact ratio. What lasted was the central mismatch between visible material and gravitationally required mass. Several uncertainties demanded caution. The first involved distance. Astronomers needed to know how far away the cluster was in order to translate its apparent size and brightness into physical quantities. Distance measurements for remote galaxies were far less secure than they later became. An error in distance could change estimates of scale, luminosity, and mass. The second uncertainty involved membership. A telescope shows objects projected onto the sky. Some galaxies that appear near a cluster may lie in front of it or behind it. Others may be passing through rather than belonging to a settled population. If an object is counted as a member when it is not, its motion can distort the estimate of the cluster's internal speed. A reliable calculation requires a reliable answer to a basic question: which galaxies are actually part of the system being weighed? The third problem was the conversion from light to mass. A galaxy's brightness does not directly announce how heavy it is. Different populations of stars produce different amounts of light for the same amount of matter. Faint stars can add mass without adding much brightness. Gas and dust may be difficult to count. Estimating mass from luminosity, therefore, requires assumptions about what is shining and what ordinary material may remain unseen. The fourth uncertainty concerned the state of the cluster itself. Virial reasoning works best when a system has had time to settle into a broad balance. A cluster that is forming, colliding, or rapidly changing may not satisfy that condition. Its galaxies can carry motions created by recent events rather than by a stable, shared gravitational structure. Applying an equilibrium method to an unsettled system can produce a misleading mass. These limitations provided serious alternatives to the most dramatic interpretation. Perhaps the cluster contained large amounts of ordinary matter that did not appear in the visible galaxy count. Perhaps its galaxies had not reached a stable state. Perhaps measurements taken from a small sample exaggerated the true spread of speeds. Science had to improve every part of the comparison before the discrepancy could be treated as a general feature of the universe. That process changed the details, but did not erase the problem. Astronomers measured more galaxies, refined distances, improved estimates of stellar populations, and studied clusters through forms of radiation beyond visible light. The ordinary matter inventory grew more complete. Hot gas between galaxies became an important part of the cluster account. Yet even when that gas and other visible material were included, clusters still required substantially more gravitating mass than their luminous contents supplied. This distinction between correcting a measurement and removing an effect is essential. Suppose an early estimate says that a system is missing an enormous amount of mass. Later work may show that some galaxies were counted incorrectly, that the distance was different, or that unseen ordinary gas supplied more mass than expected. The original estimate must then change. But if the corrected inventory still falls well short of the gravity demanded by the measured motion, the main question remains. In fact, it becomes stronger in a different way. The size of the mystery may be revised, yet its dependence on one crude mistake becomes less likely. Each correction removes a possible escape route. The argument no longer rests on trusting an old calculation. It rests on whether the discrepancy survives after known weaknesses are repaired. That is why the history cannot be reduced to a dramatic claim followed by simple confirmation. The evidence developed by being criticized. Assumptions were exposed, measurements improved, and ordinary explanations were given room to account for the result. The missing mass problem endured not by avoiding correction, but by passing through it. The method also reveals what astronomers actually mean when they say they have weighed something too distant to place on any physical scale. They do not collect all the matter and compare it with a standard weight. They measure relationships. A faster population needs a stronger binding influence. A wider system requires gravity to act across a greater region. These observations are combined through a tested physical framework to infer the mass that would produce them. The resulting weight is therefore not a direct count of objects. It is a gravitational requirement. Visible light supplies a separate estimate based on the material that can be identified. The force of the discrepancy comes from comparing these two routes. One asks how much mass the motion needs. The other asks how much known matter the observations provide. Neither route is perfect, and their uncertainties must be carried honestly. Yet when their ranges remain separated, the gap cannot be dismissed merely by pointing out that inference was involved. The correct response is to seek another system, another measurement, and another opportunity for the proposed missing mass to either appear again or fail. The question therefore survived the weaknesses of its first calculation. This is one of the most important ways a scientific problem becomes durable. An early result does not remain important because its original numbers are treated as sacred. It remains important when better observations correct those numbers, reduce known errors, include missing details, and still preserve the central effect. The Coma discrepancy also showed why a cluster could be both useful and difficult. Its enormous size amplified the gravitational problem. Many galaxies moving through one shared region offered multiple tracers instead of a single orbit. But that same complexity introduced uncertainty. A cluster is not a clean mechanical system laid out on a laboratory table. It contains galaxies, gas, evolving structures, and motions viewed from one distant direction. Every estimate depends on separating the common gravitational pattern from the disorder of a living cosmic system. For that reason, cluster motion alone could not reveal the identity of the missing mass. It could not show whether the extra gravity came from an unknown non-luminous component, underestimated ordinary material, or a failure in the assumptions used to weigh the system. It established a demand for more gravity under stated conditions. It did not place a new particle in anyone's hand. Nor did the early discrepancy prove that the same explanation had to operate everywhere. A problem seen in one kind of system might arise from conditions unique to that system. Clusters could be unusually complicated. Their members could be disturbed. Their histories could make simple calculations unreliable. If the missing mass was a broad feature of nature, rather than a special difficulty in cluster astronomy, it should appear in other systems measured by other routes. This changes how the historical episode should be understood. It is tempting to tell the story as one moment in which a hidden universe was discovered and then ignored. The real scientific value is more patient. Zwicky's work made a difficult mismatch visible. It demonstrated that the motion of luminous objects could be used to test whether their own light accounted for the gravity around them. It also exposed the assumptions that any such test would have to survive. The result was not a finished answer, but a well-formed question. How much mass must a cosmic system contain to produce the motion we observe, and how much of that mass can be accounted for by everything that shines? Once those two totals were placed side by side, their disagreement became something future observations could challenge, revise, or confirm. That is the proper local answer supplied by Coma. Visible galaxies alone did not appear able to bind the cluster under the physical assumptions being used. The conclusion remained conditional, but the condition was testable. Better distances, fuller membership lists, improved light estimates, and a clearer account of ordinary matter could weaken the gap. They improved the measurement, yet the gap remained. To make the test cleaner, astronomers needed systems whose internal motion could be followed in greater detail. Instead of treating many galaxies as points moving through one enormous cluster, they could examine motion within individual galaxies. There, speed could be measured at different distances from a clear center. The expected decline could be compared with the observed pattern step by step, rather than compressed into one estimate for an entire crowded system. If the missing pull belonged only to the uncertainty of clusters, it might fade when the measurement moved to this smaller and more orderly scale. But if visible matter repeatedly failed to supply enough gravity inside galaxy after galaxy, then the old Coma discrepancy would no longer look like an isolated historical puzzle. It would become one expression of a much larger pattern, traced across the rotating structures of the universe. The Coma cluster turned many galaxies into moving markers inside one enormous gravitational system. But its complexity left several ways for the mass estimate to go wrong. An individual galaxy offered a more detailed test. Instead of reducing an entire cluster to one broad comparison, astronomers could measure motion at many distances from a single center and watch how the gravitational pattern changed from the bright inner region to the faint outer edge. The result of those measurements is called a rotation curve. On a graph, distance from the galactic center runs in one direction, while orbital speed runs in the other. Each measured point shows how quickly stars or gas are moving around the galaxy at a particular radius. The shape of the completed curve allows astronomers to compare the motion they observe with the motion expected from the distribution of visible matter. To understand that expectation, it helps to return briefly to the solar system. Almost all its mass lies in the Sun. As distance from the Sun increases, planets travel more slowly in their orbits. The comparison is limited because a galaxy is not a single central object. Its stars and gas are spread across a broad disk, and material continues to add mass at larger radii. Yet once an orbit moves beyond most of the bright matter, a similar decline should begin. If little additional mass lies farther out, orbital speed should fall with distance. This is connected to enclosed mass, the amount of matter located inside a given orbit. Gravity acting on an orbiting object depends on how much mass is enclosed within its path and how far that object is from the center. In a bright inner region, moving outward includes more stars, gas, and dust within each wider orbit. The enclosed mass rises. But beyond most of the luminous disk, widening the orbit adds relatively little visible material. Distance keeps increasing while the known enclosed mass grows slowly. Under those conditions, orbital speeds should decline. Astronomers could test this prediction by studying light from different parts of a rotating galaxy. One side moves partly toward us, while the other moves partly away. The motion shifts familiar features in the spectrum by small amounts. Those shifts provide speeds. Repeating the measurement across the disk builds the rotation curve point by point. Building that curve requires more than finding the fastest visible object. The galaxy is tilted in space, so the measured motion along our line of sight is only part of the true orbital motion. Astronomers must account for the galaxy's orientation and identify which light belongs to each region. They must also separate organized rotation from local disturbances. A cloud may have its own motion. A spiral arm may collect gas and stars in ways that leave smaller features in the data. The aim is to recover the broad pattern beneath these local differences. This matters because the conclusion depends on the shape of the whole curve. An unusual point could come from measurement error or local structure. A sustained outer pattern across many points is much harder to explain away. The curve turns scattered spectral shifts into a continuous gravitational test, where the visible matter is concentrated, where it fades, and whether the orbital response follows the decline that concentration predicts. The work associated with Vera Rubin and Kent Ford became central to this story. Using sensitive spectroscopic observations, they measured rotation in spiral galaxies with increasing reach and clarity. Their results joined a wider body of optical and radio astronomy rather than standing as a single isolated discovery. Different researchers, instruments, wavelengths, and galaxies gradually established the important pattern. The outer regions were not slowing in the expected way. Instead of bending downward after most of the visible material had been enclosed, many rotation curves stayed roughly flat. Stars and gas far from the center continued orbiting at unexpectedly high speeds. Flat does not mean that every measured point had exactly the same value or that every galaxy followed an identical curve. Real galaxies contain structures, measurement uncertainties, and different distributions of ordinary matter. The important feature was the broad persistence of speed, where a visible mass model predicted a stronger decline. Visible stars could trace this motion only while enough starlight remained available. To move farther into the outskirts, astronomers used another messenger, neutral hydrogen. Hydrogen gas can emit radio radiation at a wavelength of about 21 centimeters. Radio telescopes can detect this signal where the bright stellar disk has become faint, allowing the galaxy's rotation to be followed across a much larger region. This extension mattered because it tested the prediction where the visible explanation should have been weakest. Far outside the crowded center, there was less starlight and less known ordinary matter to supply additional gravity. Yet the hydrogen continued moving rapidly. The luminous galaxy seemed to fade before the gravitational influence did. The logic can be reversed to ask what mass distribution would produce the observed curve. If orbital speed remains high as radius increases, then the enclosed gravitating mass must continue growing. It cannot stop near the edge of the bright disk. More gravitational influence must be present across the outer region, even though the visible contribution has become sparse. A large, diffuse halo of non-luminous matter provides a coherent provisional answer. In this picture, The bright spiral disk sits deep inside a much broader, roughly surrounding distribution of mass. The halo contributes gravity at radii, where stars and glowing gas contribute little light. As an orbit widens, it continues enclosing more halo material. That additional mass can keep orbital speeds from falling as quickly as a luminous-only model predicts. The word halo can create the wrong image if it is imagined as a thin, shining ring around a galaxy. A dark matter halo is inferred as an extended three-dimensional mass distribution. It does not mark a sharp visible boundary, and its proposed material is not gathered only at the rim. The familiar spiral remains important, but it occupies the luminous center of a gravitational system whose reach is much greater than the photograph suggests. The halo is also not inserted only to hold one outer star in place. Its distribution must influence every measured radius. Too much mass near the center would make inner material orbit faster than observed. Too little mass in the outskirts would allow the curve to fall. A useful halo model must therefore share the gravitational work with the galaxy's ordinary matter. Stars may dominate part of the inner region. Gas may make a measurable contribution across the disk, and the non-luminous component becomes increasingly important where those sources are insufficient. Astronomers adjust possible distributions and compare the resulting motion with the entire curve. The goal is not to hide any mismatch beneath an unlimited amount of invisible material. It is to find whether one physically consistent distribution can account for the pattern without contradicting the visible components already measured. Different distributions can sometimes fit similar data, which is another reason the rotation curve constrains a halo more readily than it identifies its exact form. This explanation connects directly with the mismatch introduced at the beginning. The map drawn by light gives the disk its central concentration, its arms, and its fading outskirts. The map drawn by orbital motion demands mass across a wider volume. A halo is the structure proposed to make those maps compatible without changing the ordinary law of gravity. The inference became more persuasive because it did not depend on one unusually fast galaxy. Rotation curves could be measured across many systems. Galaxies differed in size, brightness, gas content, and the way their visible matter was arranged. The details of their curves differed as well. Yet the broad mass discrepancy repeatedly appeared, particularly where the luminous contribution could not maintain the observed speeds. Repeated appearance changes the question. In one galaxy, an uncertain distance, an incorrect tilt, or an overlooked concentration of ordinary matter might distort the result. Across a varied population, the same escape must explain many independent measurements without creating new conflicts. Bright spirals, faint systems, compact distributions, and broad gas-rich disks do not present identical accounting problems. Their diversity tests whether the missing influence is tied to one unusual arrangement. The answer is not that every curve becomes a perfect flat line. The answer is that visible matter alone repeatedly struggles to supply the full gravitational pattern. Some galaxies reveal the discrepancy at different radii or with different strength, but the need for an additional explanation persists. This is what transforms the halo from a repair for one object into a common part of galactic modeling. The explanation must be flexible enough to describe real variety, yet constrained enough to remain a scientific claim rather than a label applied whenever motion is surprising. That diversity also made the problem more demanding. Any successful explanation had to do more than add an arbitrary amount of hidden mass to every galaxy. It had to reproduce the measured curve across radius and work for systems with very different visible structures. Ordinary matter still influenced the shape, A central concentration of stars could leave a feature in the motion. Gas distributed through the disk could matter. The unseen component could not simply erase the relationship between what shines and how the galaxy rotates. In fact, the close connection between the distribution of ordinary matter and observed galactic motion became one of the deepest challenges in the subject. If dark matter dominates the outer gravitational field, why do features in visible matter often correspond so closely with features in the measured motion? A successful dark matter account must explain how galaxies formed through the combined behavior of gas, stars, and halos. Any alternative account must explain not only the flat outer speed, but the full range of galactic patterns. The halo interpretation therefore gains strength without becoming an identity claim. A rotation curve can indicate how mass must be distributed under an assumed gravitational framework. It cannot reveal whether that mass consists of particles, fields, compact objects, or something not yet imagined. The curve measures a gravitational requirement. The halo is a model of where the source must be placed to meet that requirement. This is a stronger conclusion than saying astronomers merely failed to see enough stars. The outer motion does not ask only for more matter somewhere inside the galaxy. It asks for gravitational influence arranged across a region. Packing all the missing mass into the bright center would not produce the same curve. The spatial pattern matters. Each wider orbit tests how the enclosed mass has changed since the previous one. As the luminous contribution levels off, while the required mass continues rising, the gap itself develops a shape. That shape is what the halo is designed to explain. It also creates predictions that can be compared with other gravitational evidence. If the inferred matter truly occupies an extended region, a method that responds to gravity without using circular motion should find influence beyond the bright disk as well. Agreement would support the added mass interpretation. Disagreement could expose a faulty halo model, an overlooked feature of ordinary matter, or a deeper problem with the assumptions behind the curve. There was also a more basic limitation. Converting orbital speed into enclosed mass assumes that gravity behaves as expected across the extremely weak accelerations found in galactic outskirts. The same law works with extraordinary success in many settings, but the rotation curve itself cannot independently prove both the law and the unseen mass introduced through it. If the predicted motion fails, one possibility is a missing source of gravity. Another is that the rule connecting visible mass to motion changes in this regime. This does not make the two possibilities equally successful across all evidence. It shows why rotation curves alone cannot decide between them. Adding a halo preserves the gravitational law and changes the matter inventory. Altering gravity preserves the visible inventory and changes the rule of motion. Both approaches can be arranged to address parts of the same galactic discrepancy. They must therefore face evidence beyond the curve that first motivated them. Before leaving the galaxies, the local answer should remain clear. Their outer material does not slow as strongly as visible mass alone predicts. The curve implies that gravitational influence continues growing beyond the bright disk. An extended non-luminous halo explains this pattern naturally within the standard law of gravity. The photograph shows the luminous galaxy, while its motion traces a larger gravitational galaxy. But motion remains an interpretation of gravity through orbiting tracers. The next test must change the method. Instead of asking only how fast visible objects move, it can ask how gravity changes the path of light, arriving from somewhere farther away. Better still, it can look for a cosmic event in which most ordinary matter occupies one region while the strongest gravitational signal appears somewhere else. If such a separation can be measured, the missing mass will no longer be only an extra quantity inferred from speed. It will acquire a location on the sky. Gravity itself will begin drawing a map of something that contributes no visible image of its own. Rotation curves made the gravitational galaxy appear larger than the bright spiral inside it. But their conclusion came from motion interpreted through an assumed law of gravity. A stronger case needed a different kind of measurement, one that did not ask how quickly stars or gas traveled around a center. Gravity offered another messenger. It could change not only the motion of matter, but also the path of light. In the modern picture of gravity, mass and energy shape the spacetime around them. Light follows the resulting geometry. When light from a distant galaxy passes near a large concentration of mass, its route bends before it reaches us. The foreground mass acts like a lens, although it does not behave exactly like a shaped piece of glass. The amount and pattern of distortion depend on how the gravitating mass is distributed between the distant source and the observer. This effect is called gravitational lensing. Under favorable conditions, the distortion is dramatic. A background galaxy may appear stretched into an arc. Multiple images of the same source may appear around the foreground mass. This is strong gravitational lensing, where the change is clear enough to be recognized in individual features. More often, the effect is subtle. A distant galaxy may be stretched by an amount too small to interpret confidently on its own. Galaxies also possess many natural shapes, so one slightly elongated image does not reveal whether gravity changed it. Astronomers overcome this problem by studying large numbers of background galaxies. Natural orientations tend to vary, while lensing creates a shared statistical pattern. Combining many small distortions allows the foreground gravitational field to emerge from the noise. This is weak gravitational lensing. It turns the shapes of distant galaxies into a field of measuring marks. Each background source carries a small piece of information about the mass along its line of sight. When those pieces are combined through a lens model, astronomers can reconstruct a projected map of gravitating matter across the sky. The reconstruction works through pattern rather than resemblance. A concentration of mass does not make background galaxies look like the object producing the gravity. Instead, it creates a related arrangement of stretching around its position. Astronomers compare the measured shapes with the shapes expected if no common lensing influence were present. They then ask what distribution of mass would best account for the shared distortion. Repeating the process across the field produces regions where more or less projected mass is required. This is conceptually similar to learning the shape of an unseen surface from many paths bent across it, although space-time is not a material sheet. No single background galaxy carries the full answer. Confidence comes from the collective geometry. The method is valuable precisely because it does not require the foreground mass to be luminous, hot, or made from a known substance. It responds to gravity. Ordinary matter, dark matter, and any other source all contribute to the same lensing total. So separate observations are needed to identify how much of that total can be assigned to visible components. Projected is an important word. A lensing map compresses the mass distributed along the viewing direction onto a two-dimensional image. It does not show depth in the same way a nearby physical survey might. Other structures in front of or behind the target can affect the result. The shapes of the background galaxies must be measured accurately, and the model connecting distortion to mass must account for instrument effects and geometry. Even with those limits, lensing changes the investigation. Rotation curves ask how much gravity is needed to explain motion around a galaxy. Lensing asks where gravitational influence lies by measuring what it does to light from somewhere else. Dark matter does not need to emit the photons. Its proposed gravity alters photons sent by a more distant source. In this way, mass that supplies no visible image of itself can still acquire a location on the sky. A particularly revealing test occurs when ordinary matter and the inferred gravitating mass do not remain in the same place. In a relaxed galaxy cluster, galaxies, hot gas, and any dark component overlap enough that their contributions can be difficult to separate. A collision between two clusters changes that arrangement. Different components respond differently as the systems pass through one another, creating a temporary cosmic experiment. The system known as the bullet cluster formed through such a collision. Two galaxy clusters encountered each other at enormous scale. To understand what the collision reveals, three observational maps must be kept distinct. One traces the galaxies. Another traces the hot gas between those galaxies. The third is reconstructed from gravitational lensing and traces the projected distribution of mass. Each map uses a different messenger and therefore answers a different question. Visible and infrared observations locate the galaxies by collecting radiation from their stars. X-ray instruments locate gas heated to extreme conditions by recording high-energy radiation from the cluster atmosphere. Lensing begins with still more distant galaxies and asks how their light was distorted while passing through the collision region. The three maps are not interchangeable. The galaxy map does not show most of the ordinary mass. The gas map does not show every gravitating source. The lensing map does not label the kind of matter responsible for its signal. Their value emerges when they are placed in relation to one another. If all three peak in the same region, ordinary and unseen contributions remain mixed. If the maps separate in a way predicted by their different collision behavior, the collision has sorted the cluster into components and made the hidden accounting easier to test. The galaxies are separated from one another by immense distances compared with their sizes. During the cluster collision, individual galaxies can pass through the opposing cluster with relatively little direct contact. Their stars do not form a continuous material that crashes like two solid walls. The galaxy populations therefore continue onward with limited slowing from collisions between their visible members. The gas behaves differently. A large share of a cluster's ordinary matter lies not inside its stars, but in extremely hot gas spread through the space between galaxies. When the gas belonging to one cluster meets gas from the other, the two diffuse atmospheres interact. They compress, heat, and slow. X-ray observations reveal this hot material and show where much of the ordinary matter was delayed by the encounter. If the missing gravity came only from ordinary matter, the gravitational mass map should remain closely tied to the dominant ordinary component. In the bullet cluster, however, the strongest lensing regions do not center on the slowed X-ray gas. They remain closer to the galaxy populations that passed through the collision with less resistance. This separation is the central result. The map of ordinary gas and the map of gravitating mass point to different locations. Most of the cluster's baryonic material was slowed and left nearer the collision region, while most of the inferred mass continued with the galaxies. The simplest interpretation is that the dominant gravitating component, like the galaxies, interacts very weakly during the collision. It passes through, rather than crashing, heating, and stopping with the gas. The result is difficult for an explanation, based only on unseen ordinary matter. Faint stars or cold gas might be missed in a luminous inventory, but the cluster collision provides a physical sorting process. The hot gas contains most of the ordinary matter and becomes separated from the lensing peaks. Adding more ordinary material must still explain why the gravitational map follows the collisionless populations instead of the dominant collisional gas. This is why the bullet cluster is often described as unusually strong evidence for dark matter. It does more than reveal a mass total larger than the visible total. It compares locations. A baryonic component is mapped through X-rays, galaxies are mapped through their light, and overall gravitating mass is mapped through lensing. Their separation gives the unseen component a behavior as well as an amount. But the lensing map is not a photograph of dark matter particles. The colored regions often placed over images of the cluster are scientific reconstructions. They show where models infer projected mass from the distortions of background sources. The colors are chosen to make different datasets readable. No detector recorded blue clouds of dark matter floating beside pink clouds of gas. Treating the composite image as a direct picture would erase the very chain of inference that gives it scientific value. The interpretation also depends on the collision geometry and the reconstruction methods. Astronomers must estimate how the two clusters moved, how their components were distributed before impact, and how much unrelated matter lies along the same line of sight. Lensing analyses contain uncertainties. X-ray maps trace hot gas especially well, but do not represent every baryon with equal ease. The system is dynamic, rather than perfectly settled. These complications do not make the separation meaningless. They define what must be tested. If different analyses recover mass peaks away from the main gas concentration, if the locations remain stable under reasonable modeling choices, and if the collision history makes physical sense, the added mass interpretation gains strength. The evidence is powerful because two imperfect maps with different weaknesses reveal a consistent offset. Observations with the Webb Space Telescope in 2025 refined the view of the bullet cluster. Webb's sensitivity helped researchers characterize background galaxies and the cluster environment more clearly, improving the information used to study the mass distribution. This did not amount to a new direct detection of a dark matter particle. It improved an already important gravitational investigation by sharpening the objects and structures from which the lensing analysis is built. The bullet cluster is also not the only merging cluster used for this purpose. Other collisions provide comparisons with different orientations, speeds, mass ratios, and stages of encounter. They do not all produce identical maps or equally simple interpretations. That variation is useful. A conclusion that survives across multiple systems is less likely to depend on one rare geometry or one reconstruction choice. At the same time, merging clusters place limits on how freely the unseen component can interact with itself. If dark matter particles collided strongly with one another, their distribution might slow or separate from the galaxies during a cluster encounter. The observed alignment can therefore support the description of a largely collisionless component. Exact limits require detailed modeling and belong to a later discussion of properties. Here, the qualitative point is enough. The missing mass behaves differently from hot, ordinary gas. This independent evidence changes the balance of the earlier question. Rotation curves could be explained by adding halos or by changing the relation between visible matter and motion. A collision with separated maps is harder to address through a simple change to gravity alone, because the gravitational signal must still follow a different location from the dominant ordinary mass. More complex theories may attempt to reproduce such behavior, and the cluster does not eliminate every possible alternative, but it raises the burden substantially. The reason is spatial, not merely numerical. A changed gravitational rule might strengthen the pull associated with visible matter, allowing the same baryons to produce more apparent gravity than expected. In a system where all material overlaps, that can resemble an added mass component. In the collision, however, the ordinary gas and the galaxies occupy different regions. Any theory must predict where the strengthened gravitational signal should appear after that separation. If the signal remains centered mainly on the gas, it does not match the reconstructed lensing peaks. If it follows the galaxies, the theory must explain why a relatively smaller share of ordinary matter controls the map while most baryons sit elsewhere. Some modified frameworks introduce additional fields or unseen mass to meet this challenge, but doing so moves beyond the simplest claim that no extra component is required. The bullet cluster does not settle every debate, yet it forces competing explanations to reproduce a detailed arrangement instead of only a total speed or mass difference. This also demonstrates why independent evidence is more valuable than many repetitions of the same measurement. Another rotation curve can show that the galactic pattern is common, but it still shares the basic assumptions of rotation curve analysis. Lensing introduces different data and different weaknesses. A cluster collision then adds a physical separation that an isolated galaxy cannot provide. Agreement across these methods is not perfect duplication. It is convergence. Motion requests extra gravity, lensing locates extra gravity, and the collision tests how its source behaves relative to ordinary matter. Any single method may contain an error or an incomplete assumption. For all of them to point toward the same broad component, a competing explanation must address each root without solving one by breaking another. The case grows through this connected burden, not through the dramatic appearance of one colored composite image. The local answer is therefore stronger than the one supplied by orbital speed alone. Gravitational lensing can map mass that does not shine. In the bullet cluster, that map separates from most ordinary matter and remains closer to components that pass through the collision with little resistance. The result supports an additional, weakly interacting source of gravity. Yet the identity remains hidden. Lensing responds to total projected gravity. It cannot tell whether the source is one particle, a family of particles, a field, compact objects, or a deeper change in physical law. It assigns gravitational influence to a place, but it does not reveal the microscopic thing occupying that place. There is another question the collision cannot answer. Clusters are mature structures formed long after the universe began. Their galaxies, gas, and inferred dark matter have passed through billions of years of cosmic change. If the unseen component is truly fundamental to the matter inventory, its influence should not begin only after galaxies appear. It should be present in evidence from a time before clusters, before stars, and before any bright spiral could trace its gravitational surroundings. To look that far back, the investigation must leave the nearby architecture of galaxies and turn toward the oldest light that can be mapped across the sky. If dark matter was already shaping the universe then, its shadow should be written not as a dark object in an image, but as a pattern inside the first light itself. The bullet cluster showed an unseen gravitational component inside a mature structure, after galaxies had formed and gathered into enormous systems. But a collision between clusters cannot tell us when that component first became important. If dark matter is part of the basic cosmic inventory, its influence should reach farther back than galaxies. It should appear in evidence from a time before the first star had begun to shine. That evidence arrives through the cosmic microwave background, often shortened to the CMB. It is ancient radiation that has traveled through the universe for nearly all of cosmic history. In the young universe, matter and radiation filled a hot, dense environment. Light could not travel freely across great distances because photons repeatedly interacted with charged particles. The universe was not empty space containing separate glowing objects. It was an expanding plasma in which radiation and ordinary matter were closely linked. As expansion continued, the universe cooled. Electrons could remain joined to atomic nuclei, producing neutral atoms. With far fewer free-charged particles available to scatter them, photons began traveling much more freely. The radiation released from that era has stretched with the expansion of space until it now reaches us mainly as microwaves. Calling the CMB a picture of the infant universe is useful but incomplete. It does not show early stars, planets, or recognizable objects. It maps tiny differences in the temperature and polarization of radiation arriving from different directions. Those differences are extremely small, yet their statistical pattern carries information about the contents and physical conditions of the universe at the time the radiation began traveling freely. Temperature variations show where the radiation reaching us is warmer or cooler than average. Polarization records an orientation in the light created by its earlier interactions. These maps differ, and neither should be imagined as a direct view of dark objects. Dark matter does not appear as a black patch among brighter regions. Its contribution is recovered through the way gravity affected the plasma and the radiation pattern as a whole. The evidence therefore resembles a coded physical record. Scientists know the processes that can shape the code, calculate what different cosmic ingredients would produce, and compare those predictions with the measured sky. The smaller the variations appear to the eye, the more important the statistical analysis becomes. Meaning lies in their arrangement across scales, not in the dramatic appearance of any single spot. The pattern arose from a competition inside the early plasma. Gravity tried to draw matter into slightly denser regions. Pressure from radiation resisted compression. Ordinary matter, also called baryonic matter, included protons and atomic nuclei carrying electric charge. Before neutral atoms formed, those particles interacted strongly with the surrounding photons through the charged electrons. Photons pushed on the ordinary matter, while gravity pulled the combined material toward regions that were already a little denser. The result was a series of compressions and expansions called acoustic oscillations. The word acoustic refers to pressure waves, but this was not sound traveling through air. There was no room, atmosphere, or listener like the ones involved in ordinary sound. It was a physical oscillation in the tightly connected mixture of photons and baryons. Gravity compressed a region, radiation pressure resisted and drove material outward. Gravity then acted again as conditions changed. Different regions had different sizes and enough time to reach different stages of this motion before the universe became transparent. Some were caught near maximum compression. Others had expanded again. When photons stopped scattering so frequently, the state of those oscillations was preserved in the radiation. The CMB therefore contains a frozen statistical record of how the early plasma responded to gravity and pressure. Scientists analyze that record through a power spectrum. Instead of focusing only on individual warm and cool patches, they ask how strongly temperature variations appear at different angular scales across the sky. The result contains a sequence of peaks. Each peak represents modes of the early plasma that had reached particular stages of compression or expansion when the photons were released. The positions and relative heights of these peaks depend on the universe's contents. Add more baryonic matter, and the weight of the ordinary material changes the balance between compression and pressure. Change the total matter density, and the gravitational potentials and cosmic geometry affect the pattern in other ways. The full sequence, therefore, carries more information than one isolated feature. Multiple peaks must be fitted together by one consistent cosmological model. It is helpful to think of the peaks as parts of one encoded message rather than separate discoveries. A model cannot freely change the baryon density to improve one peak without affecting the others. Nor can it add total matter without changing the way gravitational wells influence the oscillating plasma. The pattern links the parameters. This is why precision comes from the full spectrum, rather than from pointing to one warm patch and calling it evidence for dark matter. Researchers compare the statistical strength of fluctuations across many scales, and the relationships among those scales restrict which combinations of ingredients can reproduce the observation. Ordinary matter leaves one kind of imprint because it takes part in both gravitational compression and photon pressure. A component that contributes gravity without joining that pressure-driven motion leaves another. The data do not print the words baryon and dark matter across the sky. They preserve physical responses that a model must separate consistently. Dark matter enters because it does not couple to photons in the same way as the charged early plasma. It contributes gravity without sharing the full pressure response of the photon-baryon mixture. While ordinary matter is pushed and pulled along with radiation, a non-baryonic component can help establish gravitational wells that influence the oscillations. Its presence changes the pattern that remains in the CMB. This makes the CMB evidence fundamentally different from a rotation curve. It does not begin with stars orbiting inside an existing galaxy. It comes from an era before the visible structures used in the earlier measurements had formed. Yet the pattern still requires more gravitating matter than ordinary baryons alone can provide within the standard cosmological framework. Measurements from the Planck mission mapped the CMB across the sky with high precision. When those observations are interpreted using the baseline model known as lambda cold dark matter, or LCDM, they yield a detailed cosmic inventory. Roughly 5% of the present cosmic energy budget is ordinary matter. About 27% is dark matter. Most of the remainder is assigned to dark energy, which is a different subject and should not be confused with dark matter. The distinction prevents a common numerical mistake. Dark matter is not 85% of everything in the universe. It is roughly 85% of the matter. Ordinary and dark matter together account for only part of the total energy budget in LCDM. Comparing dark matter only with ordinary matter gives the familiar ratio of about 5:1. Comparing it with the full cosmic inventory gives the smaller figure of roughly 27%. These percentages are not obtained by placing the universe on a scale or collecting a dark matter particle. They are model-dependent inferences. Researchers propose a cosmological model with parameters describing the contents and evolution of the universe. They calculate the CMB pattern the model predicts, then compare that prediction with observations. The parameter values that fit the data provide estimates of baryonic matter, dark matter, and other components. Model-dependent does not mean arbitrary. The peak sequence is measured in detail, and changing one component affects several parts of the pattern. A successful fit must account for those relationships together. The model also faces tests from observations outside the CMB. But intellectual honesty requires keeping the evidence category clear. Planck provides precise support for a cold, non-baryonic matter component within LCDM. It does not reveal the component's microscopic identity. LCDM earns its role by connecting many quantities through a comparatively compact framework. The Greek letter lambda represents the component associated with accelerated cosmic expansion, while cold dark matter supplies most of the gravitating matter. The model also includes ordinary matter, radiation, initial fluctuations, and the expansion history needed to calculate the CMB pattern. Its success means that one set of parameters can reproduce a remarkable range of measured features. It does not mean every assumption is immune to revision. If a different framework matched the same data as well or better, its inferred inventory might be described differently. For this reason, the percentages should always travel with the phrase within the baseline model. They are far more disciplined than guesses, yet they remain conclusions reached through a theoretical bridge between radiation and cosmic contents. The separation between strong evidence and final identity is preserved even at very high precision. There is an additional check on the amount of ordinary matter. In the universe's earliest minutes, physical conditions allowed light atomic nuclei to form. The predicted amounts of these primordial elements depend in part on the density of baryons. This process is called Big Bang nucleosynthesis. Observed primordial abundances can therefore be used to estimate how much ordinary matter was present, through reasoning independent of late galaxies and their missing light. The baryon density, indicated by nucleosynthesis, broadly agrees with the baryon density inferred from the CMB. That agreement matters because the methods rely on different physical events. One uses the formation of light nuclei in the first minutes. The other uses the pattern of radiation released much later, after neutral atoms could form. Both place the ordinary matter inventory far below the total matter density required by cosmology. This chronological separation strengthens the cross-check. Nucleosynthesis tests how ordinary nuclear material behaved when the universe was only minutes old. The CMB tests how baryons and photons behaved after expansion and cooling had carried the universe into another era. The observations, calculations, and possible sources of error are not identical, yet they arrive at a compatible limit on the baryonic supply. To replace dark matter with hidden ordinary matter, an explanation would have to change both records in a coordinated way. It would need enough baryons to provide the later gravity without producing the wrong primordial element abundances or the wrong acoustic pattern. Simply making objects faint cannot achieve that. Darkness in a telescope changes an object's visibility today. It does not erase the object's participation in early nuclear reactions or in the charged plasma. This closes an important escape route. The missing matter cannot simply be an enormous population of faint, ordinary objects that telescopes have failed to count. Dim stars, cold planets, gas, dust, and other baryonic material would still belong to the baryon inventory. Hiding their light would not remove their effect on nucleosynthesis or on the early photon-baryon plasma. The early universe limits how many baryons can exist, whether or not those baryons later become bright. The conclusion is not that every possible piece of ordinary matter has been individually located. Some baryons can remain difficult to observe in the present universe. The conclusion is that the total allowed baryonic supply is not large enough to replace the non-baryonic matter required by the combined measurements. The missing gravity is not merely missing luminosity. It points to matter with different early universe behavior. That result connects the first several layers of evidence. Cluster motion demanded additional gravity. Galaxy rotation curves distributed it through extended halos. Lensing placed gravitational mass away from most ordinary gas in a collision. The CMB and nucleosynthesis now move the argument into the early universe and separate the total matter inventory from the baryonic one. The change in scale also changes the kind of claim being made. A galactic halo is inferred around a particular visible system. A cluster lensing map assigns projected mass to a region of sky. The CMB analysis asks for an average cosmic composition capable of producing a full sky statistical pattern. These claims cannot be substituted for one another, but they can support a common explanation. The halo describes where additional gravity appears after galaxies form. The CMB describes how much non-baryonic matter is required before those galaxies exist. If the numbers and behavior were badly incompatible, the dark matter picture would fracture between early and late evidence. Instead, the component inferred from primordial radiation supplies the kind of matter later models use in galaxies and clusters. This is convergence across time as well as across method. The strength lies in the different weaknesses of these methods. Incorrectly estimating the brightness of stars could affect a galaxy's visible mass, but it cannot reproduce the CMB peak sequence. A complicated cluster collision could challenge a lensing interpretation, but it cannot change primordial element formation. A cosmological model could contain incomplete assumptions, but then an alternative must explain why independent galactic, cluster, radiation, and nucleosynthesis evidence converges on the need for additional gravity. Still, precision abundance is not identity. The CMB can tell us that a component with certain broad behavior improves the model. It can estimate how much of that component is required. It can show that ordinary baryons cannot fill the gap. It cannot tell us whether the non-baryonic component is a familiar type of theoretical candidate or something physics has not yet described correctly. Nor should the phrase cold dark matter be treated as though the CMB has measured an ordinary temperature for a known substance. Cold describes how the dominant component moves and clusters in the model, especially how freely it streams across the early universe. The full meaning and observational consequences of that property belong to the next stage of the investigation. The local answer is now clear. Within LCDM, the oldest observable radiation carries a pattern that requires substantially more matter than the allowed baryonic supply. Planck's measurements place ordinary matter near 5% and dark matter near 27% of the total cosmic energy budget. Big Bang nucleosynthesis independently supports the limited baryon inventory. The unseen component was therefore not invented only to repair mature galaxies. Its gravitational role is written into early cosmic conditions. But an inventory tells us what ingredients are needed, not what those ingredients later build. If dark matter was already present before stars and galaxies, its influence should shape the growth of structure from the earliest density differences onward. The next question is no longer whether the component existed early, it is what the universe could become because that component was there. The cosmic microwave background gives us more than an inventory. Its tiny variations provide the starting pattern from which later structure had to grow. The young universe was remarkably smooth, but not perfectly smooth. Some regions contained slightly more matter than others. Those differences were small, yet gravity could enlarge them over time. A region with a little more matter exerted a slightly stronger pull. Nearby material was drawn toward it, increasing its density and strengthening its gravity further. This is the basic engine of gravitational growth. Small differences become larger because matter attracts matter. Given enough time, a faint unevenness can develop into a concentration capable of influencing a much wider region. Ordinary matter could not follow this path freely at first. Before the universe became transparent, baryons were tied to the sea of photons through their electric interactions. Gravity pulled them toward denser regions, but radiation pressure pushed back. The same coupling that produced acoustic oscillations also prevented ordinary matter from collapsing as early or as efficiently as it otherwise might have done. Dark matter behaved differently in the Standard Model. Because it did not share the strong electromagnetic coupling between photons and baryons, radiation pressure did not drive it through the same oscillations. It still responded to gravity. Regions containing slightly more dark matter could begin developing deeper gravitational concentrations, while ordinary matter remained caught in the photon-baryon plasma. These early concentrations were not galaxies waiting fully formed in the darkness. They were growing differences in density. The word halo can suggest a finished object with a clear edge, but at this stage, it is better to imagine evolving regions where dark matter's gravitational influence was becoming stronger than average. Their growth supplied a head start. That head start matters, because gravity begins with extremely small differences and has only a finite cosmic history in which to enlarge them. If every form of matter had remained locked to radiation until the universe became transparent, the later growth of structure would have begun from a more restricted position. Ordinary matter would need to catch up after losing valuable time to photon pressure. A non-baryonic component changes the timing. It can deepen gravitational variations before baryons are free to collapse. So the later gas does not begin in a perfectly smooth universe. It encounters an existing landscape of shallower and deeper gravitational regions. The difference is not that dark matter instantly forms complete galaxies. It is that growth has already started along paths ordinary matter can later follow. The measured smallness of the early variations makes this timing a serious constraint. Any model must take the faint initial pattern and produce the much stronger structure seen later, without granting gravity unlimited time or inventing large starting clumps that the CMB does not show. When neutral atoms formed and photons began traveling freely, ordinary matter was released from its earlier coupling to radiation. Gas could then respond more directly to gravity. It fell toward the concentrations that had already begun developing. Dark matter did not create stars by itself, but its gravitational wells helped gather the ordinary material from which stars could eventually form. As gas entered a denser region, it could be compressed. Under suitable conditions, it could lose energy, cool, and become still denser. The detailed path from gas to the first stars involves complicated ordinary physics, but the broad causal sequence is clear. Dark matter establishes gravitational structure. Baryonic gas falls into it. The gas cools and compresses. Stars form from the ordinary matter, and collections of stars develop inside larger halos. This means a visible galaxy and its dark halo are not two unrelated objects placed together after formation. Within LCDM, their histories are connected. The halo guides where gas gathers, while the behavior of the gas changes the developing galaxy and can also affect the distribution of matter around it. Gravity links the luminous and invisible components throughout their growth. The process is hierarchical. Smaller concentrations form and combine into larger ones. Small early systems merge, gather more matter, and become parts of larger galaxies in groups. Groups collect into clusters. The growth is not a simple ladder followed identically by every object. Some structures merge repeatedly, some accrete matter more quietly, and local environments change the path. The broad direction, however, is from small gravitational concentrations toward a connected population of larger structures. Across the largest scales, matter does not collect into isolated points distributed randomly through space. It forms a cosmic web. Long filaments connect dense knots where clusters gather. Broad, Emptier regions, called voids, lie between them. Sheets and branching structures reflect the growth of the initial density pattern under gravity. The web develops because gravity amplifies structure unevenly. Matter flows away from regions that begin slightly underdense and toward regions that begin slightly overdense. Collapse does not occur equally in every direction. A region may compress along one direction before another, contributing to sheets and then filaments rather than forming only round, isolated objects. Where filaments intersect, more material can gather and clusters can grow. Voids become emptier in relative terms as surrounding structure draws matter away. This description remains statistical. It does not predict the name or exact appearance of every future galaxy from one visible CMB patch. It predicts the broad relationships among dense knots, connecting strands, and empty volumes. Surveys can test those relationships by mapping large populations rather than relying on one spectacular structure. The cosmic web is therefore a consequence on a different scale from a rotation curve. A halo accounts for motion around one galaxy. The web tests whether the same gravitational framework organizes matter across immense regions. Galaxies illuminate parts of this web, but they do not provide a perfect map of all matter. They form more readily in some environments than others. A bright galaxy survey therefore traces the underlying distribution selectively. Gravitational lensing offers another view because it responds to total projected mass, including matter that does not shine. Comparing galaxy positions with lensing and other measurements helps test whether visible structure follows the larger gravitational network predicted by the model. Computer simulations provide a way to connect the early pattern with the later web. Researchers begin with initial conditions consistent with measurements of the young universe. They represent matter through many computational elements, apply specified physical rules, and allow the system to evolve across cosmic time. The resulting structures can then be compared statistically with surveys of galaxies, clusters, voids, and gravitational lensing. A simulation is not a filmed reconstruction of what actually happened in one region. It is a controlled calculation of what follows from chosen starting conditions and laws. Its value lies in prediction and comparison. Researchers can vary the amount or behavior of a component and see how the resulting structure changes. If dark matter moves too freely across the early universe, small variations may be smoothed away before they can grow. If it clusters in the required way, a richer hierarchy can survive. The output is then tested through quantities that observations can measure. How strongly objects cluster at different separations, how many structures appear across mass ranges, how matter is distributed through lensing, and how empty the voids become. Agreement in one image is not enough. The model must reproduce many statistical features together. Disagreement is equally useful because it identifies which assumption, starting condition, or represented physical process may need revision. The simplest large simulations may include gravity and dark matter, while leaving out most ordinary matter processes. These dark matter-only simulations are useful for studying broad gravitational growth. They reveal halos, mergers, filaments, and large-scale clustering without attempting to calculate the full life of gas and stars. But visible galaxies cannot be understood through gravity alone. Gas can heat, cool, collide, and form stars. Young and dying stars can return energy and material to their surroundings. Activity around central regions can drive further changes. These processes are often grouped under the term feedback. Simulations that include baryonic physics attempt to represent these effects as well as gravity, making them more realistic, but also more complicated. The complication comes from interaction across scale. A simulation may cover a volume large enough to contain filaments and clusters, while the physical processes that form stars occur in much smaller regions. It cannot always follow every cloud and energetic event directly at the same detail. Researchers therefore use tested rules to represent effects that occur below the resolved scale. Those rules influence how much gas cools, where stars appear, and how energy returns to the surroundings. Changing them can alter the visible galaxy without changing the broad dark matter web. This is not permission to repair any result after the fact. Each treatment must still be calibrated, compared with multiple observations, and tested outside the conditions used to build it. The point is that a visible mismatch does not identify its cause automatically. Before blaming dark matter's microscopic nature, scientists must ask whether uncertain ordinary physics could reasonably create the difference. The distinction matters when comparing prediction with observation. If a dark matter-only simulation places too much matter in the center of a small halo, ordinary processes may later move gas and alter the gravitational distribution. If fewer small galaxies are observed than a simple simulation seems to produce, the missing systems may not all be absent halos. Some halos may have failed to form visible stars efficiently. Baryonic physics can change what becomes observable without removing the underlying dark structure. This is why broad success and local tension can exist together. On large scales, the distribution of galaxies, clusters, filaments, and lensing mass resembles the statistical patterns produced when cold dark matter grows from early fluctuations. The same framework connects the CMB starting conditions with a later universe containing a web of structure. That is a major achievement. The comparison becomes especially persuasive when no single visible tracer carries the entire result. Galaxies reveal where stars formed, but their brightness depends on baryonic history. Lensing responds to total projected mass, but its maps contain geometric and observational uncertainties. Cluster counts probe the growth of rare dense structures, while voids test the region's matter left behind. A viable history must keep these different views compatible. If a model creates the right-looking galaxy pattern, but the wrong lensing distribution, it has not solved the larger problem. If it matches the CMB, but cannot grow enough later structure, its cosmic history is incomplete. LCDM's strength is the connected path it provides from small early variations to broad late-time patterns. Its limitations are exposed by the same demand for connection. Success at one scale cannot excuse failure everywhere else, and tension at one small scale should not erase agreement across independent large-scale tests before the source of that tension is understood. This connected test is what turns the scaffolding idea from a loose metaphor into a physical account whose consequences can be measured across time, scale, and several independent kinds of observation. On smaller scales, the comparison becomes harder. Gas cooling, star formation, energetic feedback, and environmental history matter greatly. Simulations must represent processes that occur across ranges far smaller than the full volume being modeled. Different treatments can lead to different visible outcomes. A mismatch may signal incomplete baryonic modeling, an incorrect assumption about dark matter, an observational selection effect, or some combination of these. The honest conclusion is not that every observed galaxy has been reproduced perfectly. It is that a dominant, sufficiently slow-moving non-baryonic component provides a successful large-scale growth framework. The remaining tensions are scientifically valuable because they identify where the model faces its most demanding tests. They should neither be hidden nor treated automatically as proof that the entire framework has failed. The word scaffolding captures one part of dark matter's role. Scaffolding determines where a visible structure can be supported while remaining distinct from the finished surface. In a similar way, dark matter creates gravitational concentrations and a cosmic network within which ordinary matter gathers and lights up. But the analogy has limits. Construction scaffolding is rigid, deliberately placed, and often removed when a building is complete. Dark matter is none of these things. It moves, merges, responds to gravity, and remains part of the system. Ordinary matter can also influence the combined distribution. The cosmic web is not built on a motionless frame. It grows through the continuing interaction of dynamic components. The role of dark matter should therefore be stated carefully. Within the standard model, it helps structure form earlier and more strongly than baryons alone would under the same physical conditions. It supplies gravitational wells before ordinary matter is free from photon pressure, and it continues guiding growth afterward. This does not prove that no galaxy could exist under any imaginable alternative law of physics. It explains why dark matter is central to the successful LCDM account of the universe we observe. The human consequence is present, but should remain restrained. The ordinary matter that later formed stars, planets, and living bodies gathered within a structure dominated by something that did not shine. Our existence is not evidence for a particular dark matter particle. Yet the causal history described by the model places the visible world inside an older invisible architecture. This provides the section's answer. Dark matter is not merely extra weight added to galaxies after their motions look wrong. The component inferred from the early universe changes how density differences grow. It helps produce halos, guides gas, supports hierarchical assembly, and shapes the filaments and knots of the cosmic web. Its influence is written into the distribution of visible structure across the universe. But successful architecture still does not reveal the builder's material. Many microscopic possibilities could behave similarly on large scales. Simulations can show which broad patterns emerge from a component with chosen properties, but they cannot transform that component into a uniquely identified particle. The remaining discrepancies on small scales also warn that ordinary matter and dark matter cannot always be separated cleanly in the final structures. The next step is therefore to reverse the logic. Instead of asking what dark matter helps the universe build, we can ask what the finished architecture tells us about dark matter. The early pattern, the surviving small structures, the cluster collisions, the enduring halos, and the absence of light each impose a different condition. Together they begin describing a thing that science has never held. The cosmic web gives us a way to reverse the investigation. Until now, dark matter has been used to explain what the universe does. We can now ask what the observed universe demands from dark matter. Each line of evidence acts like a filter. Some possible substances pass through it, others fail. The result is not a name or a captured sample, but it is far more precise than a blank space labeled unknown. The first condition is that the dominant missing component cannot be ordinary baryonic matter. The cosmic microwave background separates the behavior of matter coupled to photons from a component that contributes gravity differently. Big Bang nucleosynthesis independently limits the amount of baryonic material. Faint stars, cold planets, and hidden gas may be difficult to see, but they still contain protons and neutrons. They would still affect early nuclear abundances and the photon-baryon plasma. There are not enough allowed baryons to supply all the missing gravity. Dark matter must therefore be mainly non-baryonic. This does not identify what it is. It tells us what broad family it cannot belong to. Ordinary material may accompany dark matter in galaxies and clusters, but it cannot replace the dominant, unseen component inferred from the early universe inventory. This negative conclusion is unusually powerful because it applies whether ordinary matter shines today or not. A dark cloud of baryonic gas may be hard to photograph. A compact ordinary object may release almost no visible light. A population of faint bodies could add mass to a local system without appearing in a simple star count. None of these possibilities changes the component's early identity as baryonic matter. Protons and nuclei participate in the physical processes that set the primordial abundance limits and acoustic pattern. The universe records their presence before they have any opportunity to become faint stars, planets, or cold clouds. The non-baryonic requirement therefore does not arise from an incomplete modern census alone. It comes from comparing two eras. The early record limits the total supply of ordinary material, while later, gravity asks for much more matter. Whatever fills most of that gap must have behaved differently from baryons when the young universe was hot and coupled to radiation. The second condition is electromagnetic darkness. No meaningful emission, reflection, absorption, or scattering of light has been securely associated with the component. If it interacted electromagnetically like ordinary charged matter, large amounts of it would alter radiation, cool, collide, and form visible or obscuring structures in recognizable ways. Instead, its established influence appears through gravity. This condition must not be turned into an absolute claim that every electromagnetic coupling is exactly zero. Observations and experiments have limited possible interactions to levels below particular sensitivities. A very weak coupling could remain. The careful profile therefore says electromagnetically dark at detected levels, not metaphysically forbidden from ever affecting a photon. Electromagnetic darkness also explains why the dark component does not simply copy the visible disk. Ordinary gas can radiate energy. As it loses energy, it can settle, compress, and participate in the formation of dense stars and thin rotating structures. A component that cannot efficiently radiate does not cool through the same channel. Its gravitational distribution can remain broad, while ordinary matter becomes concentrated and luminous inside it. This connection should remain qualitative because the exact outcome depends on formation history and the unknown component. Still, it shows that lack of light is more than a problem for telescopes. Interaction determines behavior. If dark matter absorbed or emitted strongly, the processes shaping halos, clusters, and early radiation would look different. The fact that the component remains extended and non-luminous supports a picture in which electromagnetic energy loss is highly suppressed. The profile therefore links what we fail to see with the kinds of structures gravity allows us to infer. The third condition is hidden inside the word cold. In everyday speech, cold describes temperature and the way an object would feel. In cosmology, cold dark matter refers primarily to motion in the early universe. A cold component moves slowly enough relative to the expanding cosmic setting that it does not stream freely across great distances and erase too much small-scale structure. Free streaming can be understood as the tendency of moving particles or disturbances to travel out of an initially dense region. If a component moves very quickly, it crosses small concentrations before gravity can hold them together. The early density pattern becomes smoother on those scales. Fewer small gravitational seeds survive to grow. A colder component remains more closely tied to developing concentrations. Small variations are preserved. Halos can form across a wider range of sizes, and hierarchical growth can proceed from smaller structures toward larger ones. The observed abundance and distribution of structure therefore constrain how freely the dominant component could have moved. This creates a conceptual range. Hot dark matter would move rapidly enough to wash out substantial small-scale structure. Warm dark matter would erase less, while still leaving a measurable cutoff or change below certain scales. Cold dark matter preserves more small-scale power. These labels describe broad behavior, not three confirmed substances stored at different temperatures. The evidence favors a dominant component that is sufficiently cold to produce the observed large-scale web and surviving smaller structures. Exact boundaries depend on the proposed particle or field and on which observations are used. Small galaxies, fine structure and matter distribution, and other tracers can restrict free streaming, but their interpretation may also involve complicated baryonic history. Coldness is therefore not inferred from one cosmic thermometer. It is reconstructed from which pattern survived. Imagine beginning with density variations across many sizes. A rapidly moving component crosses the smaller regions and carries their matter away, while larger patterns can remain. The final universe then lacks structure below a characteristic scale. A slower component leaves more of the original hierarchy available for gravity to amplify. Observers can search for this missing or surviving structure through galaxy populations, lensing, and matter distribution. The method again illustrates how absence must be interpreted carefully. Failing to see a small luminous galaxy does not automatically mean its dark halo was erased. Star formation may simply have failed. Strong constraints come from combining tracers that depend differently on baryonic light. The broad conclusion remains that the dominant component cannot behave like a freely streaming population that would smooth away the rich structure actually observed. The fourth condition is stability. Dark matter inferred in the early universe must still provide halos, cluster mass, and large-scale structure much later. If the dominant component decayed rapidly or disappeared, the cosmic inventory and gravitational architecture would change in ways that conflict with this continuous history. Stable does not necessarily mean that every individual dark matter entity must exist forever. A component might decay extremely slowly or transform in a way whose consequences remain within observational limits. The useful constraint is that it must be effectively long-lived across cosmic time. It must persist long enough to establish early gravitational wells and remain present in mature structures. Enduring galactic halos support this condition. The component cannot simply be a temporary force that shaped the young universe and then vanished before galaxies matured. The matter inferred from the CMB and the matter inferred from later dynamics must belong to a compatible history. Stability connects those early and late measurements. Continuity across time provides a test that no single snapshot can offer. The early universe supplies an inferred abundance. Later structure supplies gravitational mass in halos and clusters. Between them lies the growth history that simulations and surveys attempt to connect. If the dark component decayed or transformed substantially, its lost mass or released energy could alter expansion, structure, or the contents of mature systems. The allowed possibilities depend on what it becomes and how quickly the change occurs, so stability is not one simple lifetime measurement. It is a requirement that any evolution remain quiet enough to preserve the observed connection. This still leaves room for models in which a small fraction changes or a dominant component survives for vastly longer than the present cosmic age. What the evidence rejects most directly is a component too short-lived to perform both roles assigned to it, shaping early gravitational growth and remaining available to explain later mass. The fifth condition concerns collisions and self-interaction. Dark matter is often called collisionless, but the word is an approximation. It certainly interacts gravitationally. The question is whether its constituents also scatter from one another or from ordinary matter through another force. Merging galaxy clusters provide a test. In the bullet cluster, hot ordinary gas collided, slowed, and separated from the lensing inferred mass, while the mass remained closer to the galaxies. The full event does not need to be retold here. Its contribution to the profile is specific. The dominant unseen component did not behave like strongly collisional gas during the encounter. If dark matter scattered very strongly from itself, cluster collisions could slow it, spread it, or separate it from the nearly collisionless galaxies. The observed distributions therefore limit strong self-interaction, but they do not prove that self-interaction is exactly absent. A weaker interaction may produce effects too small for that system to reveal, or may become important under other conditions. This is why mostly collisionless or weakly self-interacting is more accurate than absolutely collisionless. Exact limits depend on the collision speed, geometry, original mass distributions, and the model used to reconstruct what happened. Different merging clusters can provide different leverage. Together they narrow possible behavior without reducing it to a universal zero. Halo shapes and internal distributions offer related tests. Frequent collisions among dark matter constituents could move energy through a halo and change its central density or overall form. Observed halos can therefore constrain interaction strength. Yet ordinary matter can also alter central regions through gas motion, star formation, and feedback. A profile derived from halo structure must separate these influences carefully. Substructure provides another filter. Cold dark matter models produce many smaller concentrations inside and around larger halos. The number, survival, and distribution of these structures depend on the motion and interactions of the dark component. Observations can test their gravitational influence even when they contain few or no visible stars. But visible satellite galaxies are not a direct count of all subhalos. Whether a small halo forms stars depends on ordinary gas and its environment. A mismatch between predicted dark structures and observed luminous satellites can therefore have more than one cause. It may reveal new dark matter behavior, incomplete baryonic modeling, observational limits, or a combination. The evidence now forms a compact behavioral profile. Dark matter is mainly non-baryonic. It is electromagnetically dark at observed levels. It is gravitationally active. It is sufficiently cold for the measured structure to grow. It is effectively stable across cosmic time. It behaves as mostly collisionless, although weak self-interaction remains possible. Each phrase is attached to evidence, and each contains a boundary. Non-baryonic comes from early universe accounting. Electromagnetic darkness comes from the missing light-based interaction. Coldness comes from the survival and growth of structure. Stability comes from the connection between early abundance and late halos. Limited self-interaction comes from cluster collisions and halo behavior. This is scientifically valuable because it makes dark matter falsifiable in parts. A proposed explanation that is made from ordinary baryons fails the inventory test. One that couples strongly to light fails the darkness test. One that moves too freely fails the structure test. One that decays too quickly fails the continuity test. One that collides too strongly fails cluster and halo constraints. At the same time, Passing these filters does not guarantee that a candidate is real. Several fundamentally different kinds of physical entity can share the same large-scale behavior. Gravity responds to total mass and energy without printing microscopic labels onto a rotation curve or lensing map. Two candidates can build similar halos while predicting very different rare signals in a laboratory. This shared behavior creates a form of scientific ambiguity. Suppose two possible components are both non-baryonic, long-lived, dark to light, and slow enough during structure formation. On the scale of a galaxy cluster, their gravity may look almost identical. A lensing map measures the combined result, not the internal nature of each unit supplying it. Differences may appear only in smaller structures, weak self-scattering, a rare conversion, or some interaction beyond gravity. The astronomical profile tells experiments where not to look and what broad effects must be preserved, but it cannot choose an identity by itself. This is why better gravitational maps can strengthen the existence of an unseen component while leaving the central particle question open. Precision in one category does not automatically become precision in another. Scientists can know the cosmic abundance very accurately, constrain the component's motion, and limit its collisions while remaining uncertain about its mass, internal description, or non-gravitational couplings. The mystery survives inside increasingly narrow boundaries, rather than remaining completely undefined. That distinction prevents two opposite errors: claiming dark matter is only an empty name, or claiming its physical substance is already known because its large-scale gravity is well measured. The profile is therefore like a silhouette. It gives the outline of the missing component without revealing its face. The outline can become increasingly narrow as measurements improve, but more than one identity may continue fitting inside it. Small-scale tensions make this work especially important. If the centers of some galaxies or the number of small visible systems differ from simple cold dark matter expectations, the difference may be a clue. But ordinary matter is most influential on these same scales. Gas cooling, star formation, and feedback can reshape the structures being used as tests. A responsible conclusion preserves both possibilities. The local payoff is that dark matter is no longer merely whatever supplies unexplained gravity. It is a bounded physical target with required behavior. Any successful identity must satisfy the full set of conditions across early cosmology, galaxies, clusters, and the cosmic web. Solving one anomaly is not enough if the solution breaks another scale. The profile also controls future correction. If new observations reveal strong scattering, rapid decay, or erased small structures, one or more present conditions must change. Science would not need to abandon every gravitational measurement. It would revise the description connecting them. A useful profile remains open to that possibility because each property is stated with evidence, scope, and uncertainty rather than treated as an unquestionable essence across every scale we can currently measure. Yet every property in this profile was inferred through a framework that assumes a particular relation between matter and gravity. The observations show motion, lensing, radiation patterns, and structure. The additional component is the leading way to connect them while preserving established gravitational laws. There remains another logical possibility. Perhaps the silhouette looks like matter because the rule used to translate visible matter into gravitational behavior is incomplete. Before choosing among unseen particles or fields, the investigation must test the more radical question: what if gravity itself is the missing piece? The profile built from cosmic structure seems to describe a new form of matter. but every step involved a rule connecting mass with motion, lensing, or growth. If that rule is incomplete, an apparent missing component could emerge from applying the wrong gravitational expectation. The alternative deserves to be tested at its strongest, not dismissed because it challenges the leading framework. The best-known proposal is modified Newtonian dynamics, usually called MOND. It is not the general claim that gravity might be mysterious. It introduces a specific change in how motion relates to visible mass, when acceleration becomes extremely weak. In familiar stronger conditions, ordinary gravitational behavior is recovered. Below a very low acceleration scale, the effective relationship changes. This matters in the outskirts of galaxies. Stars and gas there experience tiny accelerations, precisely where rotation curves begin demanding more gravity than visible matter appears to provide. Under the MOND approach, the visible stars and gas can produce stronger effective gravitational behavior than a standard calculation predicts. The outer material can then maintain higher orbital speeds without requiring a large halo of unseen particles around every galaxy. The proposal changes the interpretation of the same observation. Under standard gravity, a flat outer curve means enclosed mass continues increasing after most visible matter has been counted. Under MOND, the visible inventory may be broadly correct, while the expected response to that inventory changes below the characteristic acceleration. The discrepancy is moved from the contents of the galaxy to the law connecting those contents with motion. This is not achieved by assigning a separate rule to every galaxy. The scientific attraction lies in using a common transition scale across many systems. If the adjustment had to be invented independently for each curve, it would offer little more than a flexible fit. A shared scale creates the possibility of prediction. Given the baryonic distribution, the theory can estimate how the motion should depart from the standard expectation. Its success or failure can then be checked across galaxies with different sizes and brightness. MOND was designed to address the galactic pattern, and that focus produces real successes. With the observed distribution of ordinary matter and a shared acceleration scale, it can reproduce important features of many rotation curves. The theory does not merely state that outer speeds are high. It connects detailed motion with the baryonic material actually present in a galaxy. This speaks directly to a challenge identified earlier. Features in the distribution of stars and gas often correspond closely with features in measured galactic motion. If a galaxy is dominated by an independent dark halo, the tightness of that relationship requires an explanation through the history and interaction of baryons and dark matter. In MOND, the relationship is built more directly into the modified response to baryonic mass. Galaxy-scale regularities, therefore, cannot be brushed aside. They show that visible matter predicts aspects of motion with surprising power. Dark matter models must reproduce that connection through galaxy formation, feedback, and the coupled evolution of baryons and halos. MOND's ability to describe these patterns acts as a benchmark even for researchers who do not accept it as the complete theory of gravity. The fairest test begins where a proposal is strongest. Galaxies often occupy the low acceleration conditions MOND was designed to describe. A model that performs well there has identified something real about the data, even if its deeper explanation is later replaced. The regularity could mean gravity changes. It could mean baryons and dark halos develop a tighter relationship than simple pictures suggest. It could reflect a deeper law of galaxy formation that appears in both descriptions. Observations alone do not force one interpretation immediately. What they force is respect for the pattern. A successful dark matter theory cannot answer every difficult rotation curve, by adding a freely chosen halo. The halo population must emerge from a consistent cosmic history and reproduce the observed link with ordinary matter. In this sense, MOND does more than compete. It raises the standard any winning explanation must meet. But a successful explanation must travel beyond the setting that motivated it. Dark matter was not inferred only from spiral rotation curves. Clusters, lensing, the cosmic microwave background, and large-scale structure created independent demands. A replacement for dark matter must account for those observations with comparable consistency. Galaxy clusters create the first major difficulty. Changing the relation between visible matter and motion can reduce part of the discrepancy, but clusters generally retain a need for additional unseen mass. Their galaxies and hot gas do not supply enough gravitational influence under simple MOND expectations to explain every observation. The problem becomes smaller or changes form, but it does not disappear automatically. Clusters matter because they change both scale and material composition. In a spiral galaxy, stars and gas form an ordered rotating system, and the low acceleration relation can be read through a detailed curve. A cluster contains many galaxies moving in different directions, a large atmosphere of hot gas, and mass inferred through dynamics and lensing. The same modification must work for this less orderly system without choosing a new acceleration rule simply because the environment changed. If extraordinary matter is proposed, it must remain within the baryon limits established by early cosmology. If an additional non-baryonic component is proposed, then the theory has accepted at least part of the dark matter conclusion. The cluster test therefore asks whether modifying gravity truly removes the missing inventory or merely reduces how much unseen material is required in one calculation. A partial reduction is scientifically useful, but it is not equivalent to a complete explanation. Merging clusters sharpen the issue because matter is physically separated. In bullet-like systems, most baryonic mass lies in slowed hot gas, while the strongest lensing signal remains closer to the galaxy populations. A theory based only on visible baryons must explain why the reconstructed gravity does not center on the dominant ordinary component. This does not mean the original MOND formula can simply be applied to a colored cluster image and declared defeated. Lensing belongs to a relativistic description of gravity. Any complete theory must specify how space-time and light respond, not only how slowly moving stars orbit in a galaxy. Relativistic extensions of modified gravity introduce additional fields or structures to make those predictions. Those extensions can produce lensing and address observations beyond galaxy rotation. Yet added freedom brings added demands. The theory must fit galaxy regularities, cluster mass maps, the CMB peak sequence, cosmic expansion, and the growth of large-scale structure with one compatible framework. Extra fields that help in one setting can have consequences in another. Relativity matters because gravity is more than a force that changes orbital speed. It sets the geometry followed by light, helps determine how clocks and distances behave, and participates in the evolution of the universe. A modification written only for the motion of stars is therefore an effective rule, not yet a full cosmic theory. To confront lensing and cosmology, the proposal must specify a larger framework that remains internally consistent. Once new fields are introduced, those fields carry energy, evolve through time, and may cluster or influence radiation. They become observable parts of the theory, even if they were originally added to complete its mathematics. This gives researchers more routes for testing the model, but it also makes the simple slogan of changing gravity less simple. The completed theory must now explain why its added structure produces the desired galactic behavior without spoiling precision results elsewhere. The cosmic microwave background is especially demanding because its acoustic pattern separates baryonic behavior from the gravitational influence needed in the early universe. A simple low-acceleration modification, created for mature galaxies, does not automatically reproduce this pattern. A relativistic theory must calculate the evolving plasma, gravitational potentials, light propagation, and expansion history together. Large-scale structure adds a time-dependent test. The initial variations measured in the CMB must grow into the later web of galaxies, clusters, filaments, and voids. Dark matter supplies an early component that is not held back by photon pressure. A modified gravity alternative must provide another path from the same smooth beginning to the observed strength and timing of structure. That path cannot begin only when recognizable galaxies reach the low acceleration regime. It must operate consistently while the universe expands, and while radiation, baryons, and any new gravitational fields evolve. Strengthening gravity can help structure grow, but the timing and scale of that strengthening affect the CMB and the final web together. A model that produces enough late clustering may alter early potentials or lensing in unwanted ways. The task is not simply to make gravity stronger. It is to produce the measured sequence from early acoustic structure to later matter structure, while preserving the successful galaxy relation that motivated the theory. Some modified gravity frameworks introduce additional unseen ingredients to meet cluster or cosmological requirements. These may be fields, massive particles, or other components that contribute gravity while remaining difficult to observe directly. At that point, modified gravity and unseen matter are no longer strict opposites. A theory can change gravity and still require additional non-luminous content. This does not automatically make such hybrid theories illegitimate. Physics should be judged by consistency, evidence, and predictive success, rather than by whether an idea fits a simple public category. A modified theory may reveal a more accurate gravitational law, while its extra fields behave like part of the missing matter. The cost is explanatory complexity. If the original attraction was removing an unseen component, then reintroducing one to solve clusters and cosmology weakens that particular advantage. The benefit would need to come from better predictions, deeper unification, or clearer success where LCDM struggles. Comparative judgment must count both achievements and added assumptions. A theory that explains one elegant galactic relation but requires separate repairs for every larger scale has not replaced the leading framework. A theory that offers a single deeper mechanism across all scales would deserve a different verdict. This overlap is important because public descriptions often present a simple contest. Either dark matter exists or gravity is wrong. Nature is not required to choose such a clean division. Gravity may need refinement in some regime, while an additional matter component also exists. The question is, which combination explains the full evidence with the fewest unsupported additions and the strongest successful predictions? At present, particle dark matter within LCDM provides the broader economical framework. One dominant non-baryonic component helps explain the CMB, structure growth, halos, cluster dynamics, and lensing, while preserving a well-tested gravitational theory. Its success across scales is the main reason it leads, not mere attachment to convention. Leading does not mean complete. The LCDM faces tensions in the internal structure and satellite populations of some galaxies. Baryonic feedback complicates interpretation, but it can also make predictions less direct. Most importantly, the microscopic dark matter entity has not been identified. A framework can organize cosmic evidence successfully while leaving its central material unknown. Modified gravity keeps attention on these weaknesses. Its galaxy-scale performance suggests that the connection between baryons and motion may contain a deeper principle. Even if dark matter is ultimately confirmed as a particle or field, explaining why galactic regularities are so tight remains necessary. The alternative can identify a pattern that the leading model must understand, rather than merely fit. An honest comparison should therefore avoid two errors. The first is to claim that MOND explains everything and removes all need for unseen matter. Cluster and cosmological evidence make that statement too strong. The second is to claim that one difficult cluster has disproved every possible modification of gravity. Theories differ, can be extended, and must be tested through their complete predictions. The better question is comparative. How many independent observations does each framework explain? How many adjustable assumptions does it need? Does it predict new results, or only adapt after a discrepancy appears? Can the same version work from galaxies to the early universe without contradicting itself? This is why no single successful rotation curve, cluster model, or cosmological fit can decide the issue. The same framework must survive all domains together without internal contradiction. This comparison also clarifies why scientific consensus is not a vote on which mystery feels less uncomfortable. Dark matter asks us to accept a dominant component whose identity remains unknown. Modified gravity asks us to revise laws that have succeeded across many tested regimes and to construct a replacement that remains compatible with relativity and cosmology. Both carry intellectual costs. Evidence determines which cost buys the greater explanatory reach. At present, the unseen component approach connects more independent observations with one broad profile. The modified gravity approach achieves striking economy for certain galaxy relations, but generally needs more structure when it leaves that domain. This balance can change only through measurements and successful predictions, not through a preference for visible matter or discomfort with hypothetical particles. On this broader test, an additional dark component remains the leading answer. Modified gravity performs impressively in important galactic regimes, but it struggles to replace dark matter economically across clusters, lensing, the CMB, and structure growth. Some extended theories remain active, and future evidence could change the balance. The limitation remains as important as the verdict. Multi-scale success does not prove that gravity is perfectly understood in every weak field. It does not turn the dark matter silhouette into a discovered substance. It shows that preserving established gravity and adding a constrained non-baryonic component currently connects the evidence more effectively. With that alternative tested, the investigation can descend from cosmic behavior to physical identity. The required component must be dark, non-baryonic, stable, sufficiently cold, and mostly collisionless. More than one kind of entity can satisfy those conditions. The next question is no longer whether a silhouette exists. It is what possible suspects can fit inside it. The evidence has produced a silhouette, non-baryonic, dark to light, gravitationally active, sufficiently cold, long-lived, and mostly collisionless. Modified gravity does not currently replace that component across every scale. The next task is to ask what could occupy the silhouette. This is where one mystery divides into many. Dark matter is often discussed as though it were the name of a particular particle. It is not. It is a physical role that several very different entities could perform. Each candidate must pass the same cosmic filters, but candidates that look alike through gravity may behave very differently in an experiment. One historically influential family is made of weakly interacting massive particles, or WIMPs. The name describes the basic idea. These would be particles with mass that do not carry ordinary electromagnetic interactions and interact only weakly, apart from gravity. If stable, they could survive from the early universe and behave as cold dark matter. WIMPs gained attention partly through a thermal relic argument, sometimes called the WIMP miracle. In the hot early universe, hypothetical particles could have been created and destroyed through interactions with surrounding matter. As expansion and cooling continued, those interactions would become less frequent. A surviving population could be left behind. For certain masses and weak-scale interaction strengths, the remaining abundance falls near the amount cosmology requires for dark matter. The coincidence was attractive because it connected the cosmic inventory with particle physics motivated for other reasons. It suggested that new physics at an accessible energy scale might naturally leave the right relic abundance. But theoretical elegance is not observational evidence. The WIMP miracle identifies a plausible mechanism and search target. It does not show that nature selected it. WIMPs would be distinguished through rare interactions with ordinary particles, products of possible annihilation or decay, or missing energy in high-energy collisions. The exact signal depends on the model. A WIMP could fit the broad gravitational profile while having an interaction rate too small for present instruments, or it could occupy a mass range a particular detector does not test well. The family remains broad even after many simple versions are constrained. This breadth is easy to underestimate. WIMP does not name one mass or one fixed interaction strength. It groups models sharing a general style of weak coupling and massive behavior. A search can exclude a region defined by those quantities without excluding every WIMP-like possibility. At the same time, repeated failure in the most attractive regions changes scientific expectations. The original promise was not only that a WIMP could exist, but that a simple weak-scale story might make it naturally abundant and experimentally reachable. As that simple territory narrows, the family may survive while losing some of the elegance that first made it dominant. This is a legitimate shift in evidence, not a binary movement from proven to disproved. Candidate assessment must track both what remains logically possible and what remains strongly motivated. A second major family begins with the Axion. The Axion was not invented only to explain missing cosmic mass. It arose from an attempt to solve the strong CP problem, a puzzle involving why the strong nuclear interaction appears to preserve a symmetry it could have violated. The proposed solution introduced a new field whose excitations could be described as axion particles. Under suitable early universe conditions, that field could leave a large population behaving as cold dark matter. The picture differs from imagining heavy particles bouncing through space like tiny hidden stones. Axion dark matter can be treated as a coherent field spread across large regions, with particle-like behavior appearing through its interactions and detection. Axion-like particles broaden the idea. They may share similar light, weakly coupled behavior without being tied to the original strong CP solution in exactly the same way. This flexibility creates a wider landscape of possible masses and couplings. It also means that saying axion-like does not specify one complete model. Axions could be distinguished if they convert into detectable electromagnetic signals under controlled conditions, or leave astrophysical effects consistent with their coupling. Such interactions must be weak enough to preserve the observed darkness. No confirmed signal has established axions as the cosmic dark matter, but their independent theoretical motivation and ability to behave coldly keep them important. Their production history also changes how abundance is understood. The axion field need not begin in thermal balance with ordinary particles and then freeze out like the simple WIMP picture. It can store energy through its initial field configuration and later behave gravitationally like cold matter. This provides another lesson from the candidate landscape. The same present-day abundance can arise through very different early histories. Cosmological measurements tell us how much dark matter is required, while theory must explain how a proposed component reached that amount without disrupting other observations. A candidate that fits today's halo profile but produces the wrong early universe consequences still fails. The motivation, abundance mechanism, and detection channel must remain parts of one coherent account. Other candidates would move more rapidly in the early universe. Warm dark matter occupies the conceptual region between cold and hot behavior. Sterile neutrino-like candidates are one proposed route. Unlike familiar neutrinos that participate in known weak interactions, a sterile candidate would be hidden from those ordinary interactions except through possible mixing or other small effects. Its early motion could erase density variations below a characteristic scale. That makes structure formation the central test. A warm candidate might reduce the abundance of small halos or change their internal development. The same behavior that could ease some small-scale tensions can become a problem if it removes structures that observations require. This creates a narrow balance. The candidate must move enough to leave its proposed signature, but not enough to destroy the successful large-scale hierarchy. Measurements of small structures, matter distribution, and possible decay signals can restrict the model. Baryonic uncertainty complicates some tests, so apparent improvements must be evaluated across several observations. At still lower masses, dark matter may behave less like a collection of localized objects and more like a field with wave-like effects across astrophysical distances. These ultralight candidates can still supply gravity and may form broad halos, but their collective behavior could smooth or reshape structure below scales connected to their wavelength. Small galaxies and halo centers become possible laboratories. If wave-like behavior prevents matter from concentrating in the same way as ordinary cold particles, observations could reveal a characteristic pattern. Yet gas and stellar feedback can also alter the same regions. A convincing test must separate a dark field signature from changes produced by ordinary matter. Ultralight fields show why the word particle can be limiting in public discussion. Modern physics allows a substance to be described through fields and quanta without resembling grains of material. The candidate may fill space coherently while still having measurable physical consequences. It remains hypothetical until a distinguishing effect is observed and competing causes are excluded. Another possibility replaces new elementary particles with compact gravitational objects, primordial black holes. These would form from unusually dense conditions in the early universe, not from the later collapse of ordinary stars. Their origin allows them to enter dark matter accounting differently from black holes made through ordinary stellar evolution. Primordial black holes could behave as cold, long-lived, electromagnetically dark mass. But they are not an unrestricted answer. Observations constrain how abundant they can be across different mass ranges. Their gravity can magnify background stars through microlensing, disturb astrophysical systems, contribute radiation through surrounding matter, or affect other measured phenomena depending on their mass and environment. Their compactness makes the test different from a particle search. A smooth sea of microscopic particles produces gravity collectively, while a population of black holes divides the same mass into discrete objects. That difference can create rare, noticeable gravitational events. A black hole passing in front of a background source can briefly magnify its light. A population can influence the motion or survival of other systems. The absence of too many such effects limits the fraction of dark matter that can be placed in black holes of particular masses. Because each observational method is sensitive to a different range and set of assumptions, exclusions form a patchwork. The remaining gaps must be studied, but they should not be described as positive evidence. The constraints leave possible windows in which some abundance may remain allowed. An allowed window is not a detection. It means current observations have not excluded every primordial black hole contribution in that range. The possibility that they make some dark matter is different from the claim that they make all of it. These candidates also demonstrate that dark matter may not have one identity. The total abundance could contain more than one component. A particle or field might supply most of it, while compact objects supply a smaller fraction. Cosmological gravity would measure the combined mass, making a mixed inventory difficult to separate without candidate-specific signatures. The idea can be extended into a dark sector. Ordinary matter is not one particle. It includes several particles and forces nane. Section 10. A universe of possible suspects. The evidence has produced a silhouette, non-baryonic, dark to light, gravitationally active, sufficiently cold, long-lived, and mostly collisionless. Modified gravity does not currently replace that component across every scale. The next task is to ask what could occupy the silhouette. This is where one mystery divides into many. Dark matter is often discussed as though it were the name of a particular particle. It is not. It is a physical role that several very different entities could perform. Each candidate must pass the same cosmic filters, but candidates that look alike through gravity may behave very differently in an experiment. One historically influential family is made of weakly interacting massive particles, or WIMPs. The name describes the basic idea. These would be particles with mass that do not carry ordinary electromagnetic interactions and interact only weakly, apart from gravity. If stable, they could survive from the early universe and behave as cold dark matter. WIMPs gained attention partly through a thermal relic argument, sometimes called the WIMP miracle. In the hot early universe, hypothetical particles could have been created and destroyed through interactions with surrounding matter. As expansion and cooling continued, those interactions would become less frequent. A surviving population could be left behind. For certain masses and weak-scale interaction strengths, the remaining abundance falls near the amount cosmology requires for dark matter. The coincidence was attractive because it connected the cosmic inventory with particle physics motivated for other reasons. It suggested that new physics, at an accessible energy scale, might naturally leave the right relic abundance. But theoretical elegance is not observational evidence. The WIMP miracle identifies a plausible mechanism and search target. It does not show that nature selected it. WIMPs would be distinguished through rare interactions with ordinary particles, products of possible annihilation or decay, or missing energy in high-energy collisions. The exact signal depends on the model. A WIMP could fit the broad gravitational profile while having an interaction rate too small for present instruments. Or it could occupy a mass range a particular detector does not test well. The family remains broad, even after many simple versions are constrained. This breadth is easy to underestimate. WIMP does not name one mass or one fixed interaction strength. It groups models sharing a general style of weak coupling and massive behavior. A search can exclude a region defined by those quantities without excluding every WIMP-like possibility. At the same time, repeated failure in the most attractive regions changes scientific expectations. The original promise was not only that a WIMP could exist, but that a simple weak-scale story might make it naturally abundant and experimentally reachable. As that simple territory narrows, the family may survive while losing some of the elegance that first made it dominant. This is a legitimate shift in evidence, not a binary movement from proven to disproved. Candidate assessment must track both what remains logically possible and what remains strongly motivated. A second major family begins with the Axion. The Axion was not invented only to explain missing cosmic mass. It arose from an attempt to solve the strong CP problem, a puzzle involving why the strong nuclear interaction appears to preserve a symmetry it could have violated. The proposed solution introduced a new field whose excitations could be described as axion particles. Under suitable early universe conditions, that field could leave a large population behaving as cold dark matter. The picture differs from imagining heavy particles bouncing through space like tiny hidden stones. Axion dark matter can be treated as a coherent field spread across large regions, with particle-like behavior appearing through its interactions and detection. Axion-like particles broaden the idea. They may share similar light, weakly coupled behavior without being tied to the original strong CP solution in exactly the same way. This flexibility creates a wider landscape of possible masses and couplings. It also means that saying axion-like does not specify one complete model. Axions could be distinguished if they convert into detectable electromagnetic signals under controlled conditions or leave astrophysical effects consistent with their coupling. Such interactions must be weak enough to preserve the observed darkness. No confirmed signal has established axions as the cosmic dark matter, but their independent theoretical motivation and ability to behave coldly keep them important. Their production history also changes how abundance is understood. The axion field need not begin in thermal balance with ordinary particles and then freeze out like the simple WIMP picture. It can store energy through its initial field configuration and later behave gravitationally like cold matter. This provides another lesson from the candidate landscape. The same present-day abundance can arise through very different early histories. Cosmological measurements tell us how much dark matter is required, while theory must explain how a proposed component reached that amount without disrupting other observations. A candidate that fits today's halo profile but produces the wrong early universe consequences still fails. The motivation, abundance mechanism, and detection channel must remain parts of one coherent account. Other candidates would move more rapidly in the early universe. Warm dark matter occupies the conceptual region between cold and hot behavior. Sterile neutrino-like candidates are one proposed route. Unlike familiar neutrinos that participate in known weak interactions, a sterile candidate would be hidden from those ordinary interactions except through possible mixing or other small effects. Its early motion could erase density variations below a characteristic scale. That makes structure formation the central test. A warm candidate might reduce the abundance of small halos or change their internal development. The same behavior that could ease some small-scale tensions can become a problem if it removes structures that observations require. This creates a narrow balance. The candidate must move enough to leave its proposed signature, but not enough to destroy the successful large-scale hierarchy. Measurements of small structures, matter distribution, and possible decay signals can restrict the model. Baryonic uncertainty complicates some tests, so apparent improvements must be evaluated across several observations. At still lower masses, dark matter may behave less like a collection of localized objects and more like a field with wave-like effects across astrophysical distances. These ultralight candidates can still supply gravity and may form broad halos, but their collective behavior could smooth or reshape structure below scales connected to their wavelength. Small galaxies and halo centers become possible laboratories. If wave-like behavior prevents matter from concentrating in the same way as ordinary cold particles, observations could reveal a characteristic pattern. Yet gas and stellar feedback can also alter the same regions. A convincing test must separate a dark field signature from changes produced by ordinary matter. Ultralight fields show why the word particle can be limiting in public discussion. Modern physics allows a substance to be described through fields and quanta without resembling grains of material. The candidate may fill space coherently while still having measurable physical consequences. It remains hypothetical until a distinguishing effect is observed and competing causes are excluded. Another possibility replaces new elementary particles with compact gravitational objects, primordial black holes. These would form from unusually dense conditions in the early universe, not from the later collapse of ordinary stars. Their origin allows them to enter dark matter accounting differently from black holes made through ordinary stellar evolution. Primordial black holes could behave as cold, long-lived, electromagnetically dark mass, but they are not an unrestricted answer. Observations constrain how abundant they can be across different mass ranges. Their gravity can magnify background stars through microlensing, disturb astrophysical systems, contribute radiation through surrounding matter, or affect other measured phenomena depending on their mass and environment. Their compactness makes the test different from a particle search. A smooth sea of microscopic particles produces gravity collectively, while a population of black holes divides the same mass into discrete objects. That difference can create rare, noticeable gravitational events. A black hole passing in front of a background source can briefly magnify its light. A population can influence the motion or survival of other systems. The absence of too many such effects limits the fraction of dark matter that can be placed in black holes of particular masses. Because each observational method is sensitive to a different range and set of assumptions, exclusions form a patchwork. The remaining gaps must be studied, but they should not be described as positive evidence. The constraints leave possible windows in which some abundance may remain allowed. An allowed window is not a detection. It means current observations have not excluded every primordial black hole contribution in that range. The possibility that they make some dark matter is different from the claim that they make all of it. These candidates also demonstrate that dark matter may not have one identity. The total abundance could contain more than one component. A particle or field might supply most of it, while compact objects supply a smaller fraction. Cosmological gravity would measure the combined mass, making a mixed inventory difficult to separate without candidate-specific signatures. The idea can be extended into a dark sector. Ordinary matter is not one particle. It includes several particles and forces whose interactions create atoms, chemistry, stars, and complex structures. Dark matter might also belong to a hidden collection rather than one isolated species. A dark sector could contain multiple particles, internal forces, stable and unstable states, or self-interactions that remain weakly connected to ordinary matter. This possibility can produce signatures that a one-particle model lacks. Dark particles might scatter among themselves, transform, or create different structure on small scales while remaining nearly invisible electromagnetically. A weak portal between the dark sector and known matter might permit rare laboratory signals. But flexibility has a cost. A theory with many unknown particles, masses, and forces can be adjusted to fit more outcomes. That makes it harder to produce sharp predictions. Scientific usefulness requires identifying consequences that distinguish the model from simpler cold dark matter and from baryonic astrophysics. A hidden sector cannot be accepted merely because its freedom allows it to survive every null result. The candidate landscape is therefore not a flat list of equally likely guesses. WIMPs have a powerful historical connection to weak-scale particle physics, but face tightening experimental constraints. Axions combine dark matter behavior with another theoretical problem and motivate specialized searches. Warm and ultralight candidates leave structure signatures that can be tested but must preserve large-scale success. Primordial black holes are constrained across mass ranges and may contribute only within remaining windows. Dark sectors offer breadth at the cost of predictive simplicity. A useful comparison asks 4 questions of every family. Why was it proposed? Can it reproduce the measured abundance and behavioral profile? What distinctive effect would separate it from the others? What evidence currently limits or supports it? The first question measures motivation, not truth. The second establishes viability, not discovery. The third creates falsifiability. The fourth determines present scientific status. Confusing these stages produces most exaggerated claims. A candidate motivated by a famous theoretical problem is not observed because the problem exists. A viable relic abundance is not a measured relic. An allowed parameter range is not a detection. Only a reproducible signature that survives competing explanations can move an identity from suspect to established component. Each suspect translates invisibility into a different physical reason. A WIMP might fail to interact with photons because it carries no electric charge and couples only weakly through other channels. An axion could have an extraordinarily small conversion probability. A primordial black hole emits no ordinary surface light, though matter around it may reveal its presence. A hidden sector could possess interactions that largely remain within itself. None of these explanations has been confirmed as the reason cosmic dark matter is invisible. They are conditional stories. If this candidate exists with these properties, then its darkness follows from this interaction pattern. The astronomical evidence supports the need for a component and constrains its behavior. It does not transfer equal support to every identity that can be made to fit. This distinction protects the investigation from theory becoming discovery. A candidate can be elegant, solve an independent problem, and reproduce the required abundance while still being absent from nature. History gives no guarantee that the most mathematically satisfying option will be the one an experiment finds. It also explains why candidate diversity is both exciting and difficult. The same gravitational silhouette permits massive particles, extremely light fields, compact objects, or hidden families. Their masses may differ by enormous factors. Their rare non-gravitational signals may require entirely different instruments. A detector designed for one can be almost blind to another. That mismatch between instruments and possibilities prevents one universal search. A massive particle might reveal itself by striking an atomic nucleus and producing a tiny recoil. A light field might require a resonant device able to convert its stored energy into a measurable electromagnetic signal. A compact object may never touch a detector, but can expose itself by magnifying a distant star. A warm candidate may be tested most strongly through the small structures missing from the universe rather than through a laboratory collision. These approaches do not compete for the same signal. They divide the landscape according to physical behavior. Their results must therefore be reported with exact boundaries. When one experiment hears nothing, it has tested a defined combination of mass, coupling, and assumed local abundance. Another candidate can remain untouched because it would never have produced that signal. This is not an excuse that makes dark matter impossible to disprove. It is a demand to build several precise tests instead of one vague search for invisibility. As coverage grows and independent methods overlap, the space of viable identities becomes smaller and more structured. The local answer is therefore a map rather than a name. Several physical families can satisfy the broad profile, but they make different predictions about recoil, conversion, decay, missing energy, lensing, or small-scale structure. Those differences turn speculation into possible tests. The best suspect is not necessarily the one with the most dramatic story. It is the one that explains the cosmic abundance, survives every established constraint, and produces a distinctive signal that another instrument can confirm. Until that happens, candidate rankings may change as theory develops and observations improve, while the gravitational case remains separate from the unresolved contest over identity at this moment in history. The limitation is equally clear. A wide landscape can absorb disappointment by shifting attention to another candidate or unexplored range. To make progress, every search must state which assumptions it tests and what a null result excludes. Failure to find one suspect cannot be treated as failure of the entire dark matter case. The next challenge is experimental. How can an instrument listen for a component whose shared feature is an extraordinary reluctance to interact? The answer requires detectors that do not try to photograph darkness. They wait for the faint traces left when an unseen entity transfers momentum, changes form, disappears from an energy account, bends light, or alters structure. Science must build ears for a universe that refuses to speak through ordinary light. The candidate map does not lead to one universal dark matter detector. Each identity predicts a different trace. The experimental problem is therefore not to photograph darkness, but to identify what a particular candidate would change if it passed through matter, transformed, decayed, or influenced another measurable system. For a WIMP-like particle, one possibility is a rare collision with an atomic nucleus. Dark matter is expected to pass through Earth continuously under this hypothesis, but almost every particle would cross ordinary material without interaction. A detector must contain enough target material, remain quiet for long periods, and distinguish a possible collision from a much larger number of ordinary events. This is why leading direct detection experiments are built deep underground. Cosmic rays constantly strike Earth's atmosphere and surface, producing particles that can enter a detector and imitate rare signals. Layers of rock absorb much of this activity. Depth does not stop dark matter if it interacts as weakly as proposed, but it greatly reduces the noise from known particles. Underground location is only the first layer of silence. Detector materials are selected and screened to reduce natural radioactivity. Additional shielding surrounds the target. Instruments record activity that might identify a background event. The challenge is not simply detecting tiny energy deposits. It is understanding every ordinary process capable of producing them. Liquid xenon provides one important target. A detector contains a large volume of xenon kept in liquid form and monitored for brief signals. If a WIMP collided with a xenon nucleus, the nucleus could recoil, transferring energy into the surrounding liquid. That recoil would not produce a visible scratch or moving track. It would create small amounts of light and electric charge. The immediate flash is called scintillation. The interaction can also free electrons from xenon atoms. An applied electric field moves those electrons upward, where they can produce a second light signal. Measuring both responses gives more information than either alone. The timing and pattern help estimate where the event occurred inside the detector. The relative size of the two signals helps distinguish a nuclear recoil from an electronic recoil. A WIMP is generally expected to scatter from a nucleus in the standard search, while many radioactive backgrounds interact mainly with electrons. The distinction is statistical rather than perfect, but it reduces the background entering the final analysis. Three-dimensional position is valuable because a genuine candidate should be able to interact throughout the liquid, while many unwanted events enter from surfaces or nearby components. An event reconstructed close to a wall can be treated differently from one deep inside the target. The detector also records how signals are spread across its sensors, providing checks on whether the event resembles a real interaction in the xenon or an instrumental effect. No single feature makes the decision. Analysts combine energy, signal ratio, position, timing, and data quality conditions to define a population worth comparing with the signal model. This layered selection illustrates the central challenge of rare event physics. The desired interaction may be simple, but proving that an event belongs to it requires showing why every more ordinary origin is unlikely. Position reconstruction supports another strategy called a fiducial volume. Events near the detector's outer surfaces are more likely to be influenced by surrounding materials or imperfectly understood boundaries. Xenon closer to the edge acts partly as shielding. Analysts define a cleaner inner region as the main search target, sacrificing some volume to gain a quieter sample. Even the inner region is not empty of known events. Radioactive contaminants, particles entering from outside, interactions connected with detector materials, and eventually neutrinos can create signals. Each background has an expected distribution in energy, position, and signal type. Researchers build models from calibration data, physical knowledge, and control samples. Calibration gives the detector known kinds of interactions and measures its response. These data show how much light and charge different energies produce, and how nuclear and electronic recoils tend to separate. Control regions contain events useful for testing backgrounds without relying on the most sensitive search region. Simulations connect measured material properties with expected activity. None of these tools makes the background perfectly known. Their purpose is to estimate both the expected number of events and the uncertainty around it. That uncertainty enters the final statistical comparison. A claim is credible only if an apparent signal cannot be absorbed by a reasonable change in the background model. More exposure helps only when understanding improves with it. A larger detector that collects proportionally more unexplained noise is not automatically a better dark matter experiment. The search then asks whether the recorded events are consistent with this background model or contain a statistically meaningful excess resembling the candidate signal. One unusual event is not enough. A rare background can look surprising while remaining fully compatible with expectation across a long exposure. Significance depends on the complete dataset and the uncertainty in the model. To protect this judgment from unconscious bias, experiments can use blinded analyses. Information from the region most likely to contain a signal is hidden or altered, while researchers choose event selections, background models, and statistical procedures. The analysis is fixed before the relevant data are revealed. Blinding cannot remove every error, but it prevents choices from being quietly adjusted to make an interesting fluctuation appear stronger. The procedure also separates discovery from storytelling after the fact. With enough variables, analysts could unintentionally choose cuts that preserve an interesting group of events while removing nearby background. A blind design forces those choices to be justified using calibration, simulations, and side regions before anyone knows how they affect the possible signal. After unblinding, unexpected events can still require investigation, and genuine mistakes can still be corrected transparently. What should not happen is a silent redesign whose only purpose is to increase significance. The method protects both outcomes. It makes a positive excess more trustworthy, and a null result more informative, because the search conditions were not selected after seeing the answer. Direct detection is not a generic test of all dark matter. Its sensitivity depends on particle mass, interaction type, coupling strength, detector threshold, and assumptions about the local halo. A heavy particle and a very light particle transfer energy differently. An interaction with nuclei may be invisible to a search optimized for electrons. An exclusion must therefore state the model it tests. Astrophysical assumptions enter because the predicted rate depends on how much candidate matter passes through the detector and how quickly it moves relative to Earth. A standard halo model supplies a practical baseline, but the real local distribution may contain uncertainty. Particle assumptions then determine how a collision rate changes with nuclear properties and recoil energy. Detector assumptions describe which of those recoils can be recorded. An exclusion curve combines all three layers. This does not make it arbitrary. It makes its meaning conditional. If the assumptions change, the exact boundary may move. The observed data remain, but their translation into candidate mass and coupling must be recalculated. Clear reporting allows another experiment using a different target or threshold to test the same region from another angle. Indirect detection looks elsewhere. If dark matter particles annihilate with one another, or decay, they might produce known particles or radiation. Researchers search gamma rays, neutrinos, antimatter, and other possible products in regions where dark matter is expected to be concentrated. The difficulty is that ordinary astrophysical sources can produce similar signals. A possible excess must match a consistent spatial and energy pattern and survive uncertain modeling of the source region. It must also agree with limits from other targets. A bright signal is not automatically persuasive if conventional objects or processes can explain it. Collider experiments reverse the logic. Instead of waiting for cosmic dark matter to arrive, they use high-energy collisions that might create new invisible particles. A detector cannot record a particle that escapes without interaction, but it can measure an imbalance in momentum or energy carried by visible collision products. The missing amount suggests that something unseen left the event. Known particles can also carry away energy, and detector imperfections can create imbalance. Collider searches, therefore, compare event patterns with detailed background predictions. Even a discovery of a new invisible particle would not automatically prove that it supplies cosmic dark matter. Its stability and cosmological abundance would need separate confirmation. Axion searches require another style of instrument. Because an axion field may be extremely light and coherent, waiting for a nuclear recoil is often the wrong approach. Experiments attempt to convert axion energy into a detectable electromagnetic signal under controlled conditions, frequently using resonance to strengthen a very narrow response. A resonance search listens across possible frequencies rather than covering every axion mass at once. The instrument must be tuned through a range while remaining sensitive to faint power above noise. Other axion experiments test different sources or couplings. A null result closes only the region to which that design was sensitive. Compact objects, such as primordial black holes, are tested mainly through gravity. Microlensing surveys monitor large numbers of background stars. If a compact object passes close to the line of sight, its gravity can temporarily magnify the star. The duration and rate of events constrain compact object populations across particular mass ranges. Lensing surveys must distinguish the desired pattern from variable stars, ordinary lenses, incomplete observing coverage, and assumptions about object distributions. Once again, an absence of expected events becomes a quantitative limit rather than a statement that nothing was learned. Cosmic structure can also serve as a detector. Warm or ultralight candidates may suppress or reshape small-scale matter patterns. Galaxy populations, lensing, and other gravitational observations can search for those effects. These methods access candidates that may never produce a laboratory collision, but their interpretation must separate dark physics from baryonic history. The search program is therefore complementary. Direct detectors listen for deposited energy. Indirect observations seek products of annihilation or decay. Colliders look for missing momentum. Axion instruments seek conversion. Microlensing tests compact objects. Structure observations test how dark matter moved and clustered. Complementarity matters because the weaknesses differ. A direct detector depends on the local halo, but does not require dark matter to annihilate. An indirect search can examine dense cosmic regions, but must model ordinary astrophysical emission. A collider controls the initial collision, but cannot establish whether an invisible product survives across cosmic time. Structure probes test the accumulated gravitational outcome, but may struggle to separate baryonic effects. If two methods point to the same candidate properties despite these differences, the combined case becomes stronger than either result alone. If they conflict, the disagreement may expose a background, an incorrect abundance assumption, or an incomplete model. No channel covers the full silhouette. Their assumptions overlap only partly, which makes agreement especially valuable. A credible discovery would require a signal inconsistent with known backgrounds, behavior matching a specific model, and confirmation by another dataset or experiment. Where possible, the inferred mass and interaction strength should agree across channels. One unexplained excess is a reason for investigation, not a completed discovery. Instruments develop unknown backgrounds. Statistical fluctuations occur. Astrophysical models remain imperfect. Repetition under changed conditions helps distinguish a physical signal from a feature unique to one analysis. Confirmation does not always require identical equipment, but it requires a compatible physical story. A second target may respond at a different rate while implying the same candidate mass and coupling. An indirect signal may appear in locations where the same model predicts higher abundance. A collider may produce an invisible state with matching interactions, though cosmology must still show that it is stable and plentiful. Independent consistency closes alternatives. If a signal appears only in one material, one season, one analysis choice, or one poorly modeled region, ordinary explanations remain plausible. Dark matter would be a new component of nature, so the standard of evidence must match the scale of the claim. Null results are equally important when their scope is stated correctly. If an experiment is sensitive to a defined range and finds no excess, it limits how strongly candidates in that range can interact. It may rule out a simple model or force its coupling lower. It does not erase candidates that produce different signals. The word null can sound like an empty outcome, but the experiment has compared two possible worlds. In one, a candidate with a stated mass and coupling produces a predicted distribution of events on top of background. In the other, only known backgrounds appear. If the first world would have created a signal larger than the data allow, that candidate point is excluded at a stated confidence level. Repeating this calculation across masses and couplings creates a boundary. The region beyond it is not rejected by silence alone. It is rejected because the apparatus was demonstrably capable of hearing the predicted signal and did not. This is measured absence within scope, not universal proof of non-existence. This is how invisibility becomes experimentally testable. Dark matter need not shine. It may transfer momentum to a nucleus, deposit energy in electrons, convert into a photon, escape a collider, magnify a star, or alter the cosmic web. Each trace turns one hypothetical identity into a measurable prediction. The limitation is built into the method. Every instrument listens within a finite range of mass, coupling, energy, time, and assumed astrophysical behavior. The full search is a patchwork whose gaps remain real. Progress comes from shrinking those gaps deliberately. Larger targets increase the chance of a rare interaction. Lower thresholds extend sensitivity toward lighter candidates. Cleaner materials and better models reduce uncertainty. Longer observations test rarer events, while different target elements change the response to particular couplings. No improvement guarantees discovery. Each one enlarges the region in which silence has a precise meaning. The search becomes more powerful, not because scientists assume dark matter must eventually appear, but because more hypotheses are forced to make contact with data under controlled conditions. That precision is the true experimental answer to invisibility. Not seeing the component directly, but defining exactly what it would have changed, and showing whether nature made that change inside the tested range at all. The next question is what this increasingly sensitive patchwork has heard. After years of quieter detectors, larger targets, stronger background control, and multiple channels, have the leading experiments found the expected signal? Or has their silence changed? Which suspects remain believable? The last section established that silence becomes evidence only when an experiment was capable of hearing a defined signal. Modern liquid xenon searches have now reached that condition across important parts of the WIMP landscape. Their result is not an empty detector. It is an increasingly precise absence of the recoils that several once-favored models predicted. The historical expectation behind these searches was unusually strong. A stable particle with roughly weak-scale interactions could emerge from the early universe with an abundance near the amount cosmology requires. The same interaction might allow an occasional collision with an atomic nucleus. Dark matter could therefore solve a cosmic problem while remaining accessible to carefully shielded laboratory instruments. This possibility drove detectors toward greater sensitivity. Targets became larger. Materials became cleaner. Background models became more detailed. Exposures grew longer, and analysis procedures became more resistant to bias. Each improvement increased the number of WIMP models that would have produced a detectable signal. Sensitivity is cumulative, but not automatic. Doubling observing time helps only if the detector remains stable and the added data can be modeled. Increasing target mass helps only if events throughout that mass can be located and backgrounds controlled. Lowering an energy threshold opens sensitivity to lighter particles while often exposing new instrumental effects. The modern limits are therefore achievements in measurement as much as in size. They represent years spent learning how ordinary events imitate the desired recoil and how to quantify what remains uncertain. The absence becomes impressive because the apparatus was made capable of recognizing a signal that earlier experiments could not have separated from noise. The Lux-Zeppelin experiment, known as LZ, reported a search using a total exposure of approximately 4.2 ton-years collected across 280 live days. Exposure combines target mass with observing time. It describes how much xenon was available to receive possible interactions and for how long, after the requirements of the analysis are applied. After its blinded analysis and background evaluation, LZ found no evidence for an excess over the expected backgrounds. Events were recorded, as they are in any real detector. The conclusion was that their number and distribution did not require an additional WIMP signal. LZ used this result to set world-leading constraints on the tested spin-independent and spin-dependent WIMP nucleon interaction models across relevant masses. Spin-independent describes a common model in which the interaction can add coherently across a nucleus. Spin-dependent interactions relate differently to nuclear spin. These labels define search assumptions, not two exhaustive ways dark matter must behave. For the standard spin-independent model, LZ's strongest reported exclusion reached approximately 2.1 times 10 to the minus 48 square centimeters at a WIMP mass near 36 giga-electronvolts divided by the speed of light squared. The boundary was stated at 90% confidence. The tiny area is not a physical WIMP size. It represents an interaction cross-section, a way of expressing how likely the proposed scattering is under the model. A smaller allowed cross-section means the particle must interact more rarely. At the most sensitive mass, models predicting stronger scattering than the limit would likely have produced more signal-like events than LZ observed. Confidence level must also be interpreted correctly. A 90% confidence exclusion is a statistical statement generated by the analysis procedure under specified models. It does not mean scientists are 90% certain dark matter is absent, nor does it assign a 10% chance that the excluded particle exists. It describes how the experiment converts its data and uncertainties into a boundary expected to perform in a defined way across repeated hypothetical datasets. The language is technical because rare event conclusions must carry their statistical conditions. For a general audience, the practical meaning is that the rejected model predicts a signal inconsistent with what LZ recorded at the collaboration's chosen standard. The limit becomes strongest where the detector's target and threshold are especially responsive to the proposed recoil. At lower or higher masses, sensitivity changes, so the curve rises. Quoting only the best number without its mass, interaction model, and confidence level would make the result sound more universal than it is. XENONnT supplied an independent large liquid xenon test. Its combined WIMP search used about 3.1 ton-years of exposure and a blind analysis focused on nuclear recoils. It also found no significant excess above the expected background. The experiments use related principles and the same target element, but they are not one duplicated dataset. Their detector designs, operating histories, calibrations, background conditions, event selections, and analyses differ. Agreement between their null results therefore provides a valuable cross-check of the liquid xenon search program. Independence here is a matter of degree. Because both instruments use xenon, they share some nuclear response assumptions and sensitivity patterns. A candidate poorly matched to xenon may evade both. Yet their separate apparatus and background histories make it less likely that one detector-specific mistake explains the common absence of a strong signal. True complementarity grows further when experiments use different target materials or search channels. If xenon, another nucleus, collider data, and indirect observations all reject the same model through different physics, the surviving space becomes narrower. For now, LZ and XENONnT provide two leading measurements within one especially powerful approach. They do not represent every way of listening. An exclusion curve summarizes this information across candidate masses. For each mass, the experiment calculates which interaction strengths would have produced a signal incompatible with the observed data. The resulting line separates excluded model points from those that remain allowed under the chosen assumptions. Those assumptions matter. The curve depends on the form of the particle interaction, the expected recoil distribution, the detector response, and a model for the amount and speed of dark matter near Earth. Change the interaction from nuclei to electrons, alter its dependence on momentum, or change the local halo distribution, and the numerical boundary can move. This does not make the result weak. Within its stated model, it is a powerful measurement. It means that a WIMP with the tested mass and a cross-section above the boundary cannot make the expected local dark matter population without producing too many events. The correct conclusion is conditional but sharp. These results place serious pressure on simple canonical WIMP stories. Regions once considered natural and reachable have been tested without the expected nuclear recoil excess. The interaction cannot remain as strong as those models proposed. Some models are excluded. Others must move toward weaker couplings, different masses, different interaction channels, or more complicated particle histories. Moving the coupling lower has a direct experimental consequence. The smaller the scattering probability, the more target mass and observing time are needed to expect the same number of interactions. Background knowledge must improve at the same time. A theory can remain viable below the current line, but it may become much harder to test through nuclear recoils. This motivates new materials and channels, rather than endless scaling of one design. It also raises a fair question about theoretical economy. A candidate originally attractive because it could be naturally detected loses some of that attraction if its interaction must be repeatedly reduced without another reason. This changes the meaning of the original WIMP miracle. The thermal abundance coincidence remains an important theoretical observation. But the simplest connection between weak-scale physics and detectable nuclear scattering has become harder to maintain. A model can survive by reducing or altering the interaction, yet each adjustment may weaken the economy that first made the candidate compelling. Scientific probability is not assigned by logical survival alone. A model can remain mathematically possible after its most natural region is excluded, but researchers may reasonably regard it as less compelling. Conversely, a candidate with a narrow prediction that survives a difficult test gains credibility even without detection. Null results therefore reshape priorities. They change which detectors are built, which interaction models receive attention, and which theoretical assumptions are reconsidered. This is progress, even when no new particle appears. The field learns that nature, if it contains a WIMP, has not chosen several of the simplest versions researchers expected to find first. None of this means all WIMPs are ruled out. The family covers broad masses and interactions. A particle may scatter below current sensitivity or through a channel to which xenon nuclear recoil searches respond poorly. The experiments exclude specified regions, not the word WIMP in every possible theory. The results say even less directly about candidates built for different signals. Axions and Axion-like fields require conversion or other specialized searches. Ultralight fields may reveal collective or structure effects. Primordial black holes are tested through gravity across mass windows. Dark sectors can contain interactions absent from the standard recoil model. Most importantly, a null WIMP search does not erase galaxy rotation curves, cluster lensing, the CMB acoustic pattern, nucleosynthesis limits, or the growth of the cosmic web. Those observations created the case for an unseen component without assuming that component was a standard WIMP. Laboratory silence increases uncertainty about identity. It does not reverse the measured gravitational discrepancies. The separation can be expressed as two linked questions. Does the universe behave as though an additional gravitating component exists? Multiple astronomical and cosmological probes answer strongly within the leading framework. Is that component a WIMP with a standard nuclear scattering interaction in the tested region? The new experiments answer no at their stated confidence. Confusing the questions produces opposite exaggerations. One exaggeration treats cosmic evidence as proof that a WIMP must appear. The other treats failure to find a WIMP as proof that the cosmic evidence was mistaken. The disciplined position allows confidence to rise at one level while falling at another. As detectors become more sensitive, known neutrinos create a new difficulty. Neutrinos can scatter from nuclei and produce recoils resembling the signal expected from some WIMPs. Unlike radioactive contamination, this background cannot be removed simply by building with cleaner materials. Neutrinos are real particles arriving from natural sources. This region is sometimes called the neutrino fog. The name is better than the older image of a solid floor, because the challenge is not an absolute wall. WIMP and neutrino events may differ statistically in energy, timing, direction, target response, or combined datasets. Extracting a signal becomes harder and may require more exposure or new detector strategies, but it is not logically impossible. The fog analogy emphasizes overlap rather than total blindness. A few recoil events may be difficult to assign individually because a neutrino and a WIMP can leave similar deposits. Across a larger sample, however, their expected distributions may differ. Measurements of neutrino sources improve the background prediction. Detectors with directional sensitivity could use the directions from which signals arrive. Different nuclei could respond differently to the same candidate. The challenge shifts from eliminating background to separating two populations statistically. Discovery remains possible, but the required evidence and exposure rise. The neutrino background also changes the meaning of progress. Increasing target size may collect more possible WIMP events and more neutrino events together. Better discrimination, multiple target materials, directional information, and complementary search channels become increasingly valuable. Sensitivity must grow through understanding, not mass alone. Repeated null results have therefore diversified the search. WIMPs remain important, but they no longer monopolize the field. Axion experiments cover different masses and couplings. Lower threshold detectors pursue lighter particles. Astrophysical structure tests warm and ultralight models. Microlensing and other observations constrain compact objects. Collidors and indirect searches continue examining complementary signatures. This strategic shift is healthy because the candidate profile never required one preferred identity. It reduces the risk that an entire field depends on a single theoretical fashion. But a broader landscape also creates a scientific danger. If every null result is answered only by inventing a weaker interaction or moving to another untested candidate, the explanation can lose predictive sharpness. There is no simple numerical point at which flexibility becomes excessive. The judgment depends on whether new versions arise from independent theory and make fresh predictions, or are introduced only to escape an exclusion. Axions remain motivated partly by a separate problem in particle physics and require different experiments. They are not merely WIMPs renamed after failure. Primordial black holes make distinct gravitational predictions. A dark sector can be scientifically useful if its internal rules generate constrained signatures. The landscape becomes unproductive only when candidates are defined so loosely that every possible result is compatible. Good science keeps the boundaries visible. This experiment tested this signal. This model survived for this reason, and this future measurement could still rule it out. A viable research program must therefore do more than preserve possibility. Each candidate should make clear predictions, identify the region where it can be tested, and accept exclusion when those predictions fail. Flexibility is useful when it reflects genuinely distinct physics. It becomes a weakness when it prevents any observation from counting against the idea. The local answer is balanced. LZ and XENONnT did not detect a significant WIMP-like nuclear recoil excess in these datasets. They set powerful limits that severely narrow important spin-independent and spin-dependent parameter regions. They weaken simple WIMP stories that predicted accessible interactions. Their result should also change the emotional meaning of silence. At the beginning, dark matter seemed frightening because most matter refused to appear in light. Underground, scientists created another opportunity for it to become visible through consequence. They surrounded tons of xenon with shielding, reduced backgrounds, waited across hundreds of live days, and defined the response expected from a collision. The anticipated excess still did not emerge. This does not make the component more hostile or supernatural. It makes the boundary of knowledge sharper. Gravity announces that something is missing from the visible inventory, while laboratory matter refuses to identify the source through this particular interaction. The universe is not merely dark, it is selective about which questions current instruments can answer. That selectivity is informative. A strong nuclear coupling would have linked the cosmic component to ordinary matter often enough for these detectors to notice. The data now say that such a link, for the excluded masses and models, is too strong to describe nature. Invisibility has gained another measured layer. Not only no ordinary light, but no nuclear recoil excess at interaction strengths the experiments could test. The deeper cause remains unknown, but its possible forms have been narrowed. They do not show that the universe contains no dark matter. They do not eliminate all WIMPs or candidate families with different signatures. Their silence moves the deepest uncertainty from cosmic existence toward microscopic identity. This is the consequence of modern non-detection. Confidence is redistributed rather than simply destroyed. Confidence in several accessible WIMP models falls. Confidence in the experimental limits rises. The gravitational phenomenon remains supported by evidence outside the laboratory. Meanwhile, attention spreads toward weaker couplings, lighter fields, compact objects, hidden sectors, and more precise astrophysical tests. The mystery becomes less centered on whether extra gravity appears and more centered on what physical reality produces it. This prepares the final synthesis while preventing experimental silence from becoming a universal conclusion about everything. That movement creates the final scientific problem. We know how the unseen component behaves across galaxies, clusters, primordial radiation, and cosmic structure. We know several things it cannot easily be. We know that some favored laboratory signals have failed to arrive. What, then, can the title's phrase "invisible for a reason" honestly mean? The answer must separate a measured absence of light from an unknown underlying cause. It must distinguish the strong gravitational case from the unconfirmed candidate stories. Only then can the investigation state what science knows, what it infers, what it models, and where explanation still ends. The silence inside modern detectors has not returned us to the beginning. We are not left with an empty label and no evidence. Instead, the investigation has separated two questions that once seemed like one. The first asks whether the universe contains gravitational influence that visible matter cannot supply. The second asks what physical entity produces it. Evidence answers the first far more strongly than the second. The case begins with direct measurements. Astronomers record the light of galaxies, the speeds of stars and gas, the motion of galaxies in clusters, the shapes of lensed background objects, the X-ray emission of hot cluster gas, and the temperature pattern of the cosmic microwave background. Underground detectors record flashes, charge, positions, energies, and backgrounds. These are observations. They are not yet dark matter itself. The next layer is strong inference. Visible mass does not produce enough gravity to explain galaxy rotation under established laws. Clusters repeat the discrepancy. Lensing locates more gravitating mass than luminous material supplies. In merging clusters, most ordinary gas separates from the main lensing inferred mass. These independent consequences point toward an additional component. Their independence matters more than the number of examples. Rotation curves could be challenged through assumptions about galactic motion. Cluster dynamics could be challenged through equilibrium and membership. Lensing has projection and reconstruction uncertainties. A merging cluster has a complicated collision history. None is perfect, yet their limitations do not align in a way that easily creates the same false component everywhere. One method asks how objects move. Another asks how background light bends. Another compares the location of hot baryonic gas with total gravitating mass. Agreement among them forces an alternative to explain several physical relationships at once. This is why the inference is stronger than the most famous image or curve used to illustrate it. The early universe strengthens that inference through a different route. Within the standard cosmological framework, the acoustic pattern in the CMB requires more matter than baryons can provide. Big Bang nucleosynthesis independently limits the ordinary matter inventory. The additional component cannot simply be faint stars, hidden planets, or cold ordinary gas. Structure growth connects this early component with the later universe. A sufficiently cold, long-lived, mostly collisionless form of matter allows small early differences to grow into halos and the cosmic web. Galaxies illuminate parts of that older gravitational architecture. Simulations and surveys test the connection without revealing the microscopic substance. These conclusions belong partly to a third layer, model-dependent knowledge. The percentages assigned to ordinary matter and dark matter come from fitting observations within LCDM. Halo distributions come from translating motion and lensing through gravity. The conclusions are precise and testable, but they remain attached to assumptions. Model-dependent does not mean invented. It means the bridge from data to conclusion is visible and open to challenge. The bridge earns confidence by making linked predictions. A chosen matter density affects the CMB peaks, later structure, cluster abundance, and lensing. A halo distribution affects more than one measured point in a galaxy. Researchers cannot change every conclusion independently without consequences. If a replacement model uses different ingredients, it must recalculate the full chain and match the observations at least as well. This is what keeps model dependence from becoming free interpretation. Assumptions are permitted because they are exposed to tests. They remain provisional because no successful model becomes identical to reality merely by fitting present data. Modified gravity challenges that bridge most effectively in galaxies, where it reproduces important relations between baryons and motion. But clusters, separated lensing maps, the CMB, and structure growth demand a broader account. At present, an additional non-baryonic component connects those scales more economically than a gravity-only replacement. This is a comparative scientific judgment, not proof that gravity can never change. Candidate identities occupy a fourth layer. WIMPs, axions, ultralight fields, warm candidates, primordial black holes, and dark sectors are possible occupants of the profile. Their motivations can be strong, and their predictions can be tested. None has been confirmed as the dominant cosmic component. The LZ and XENONnT results sharpen this distinction. Their null WIMP searches exclude important regions under specified assumptions. They weaken simple particle stories that should have produced nuclear recoils. They do not erase the lensing maps, rotation curves, early universe inventory, or cosmic web. A failed identity test is not a failed existence test when the existence case comes from different evidence. We can now answer the title directly. Dark matter is invisible because it has no detected meaningful interaction with electromagnetic radiation. It does not measurably emit, absorb, reflect, or scatter light in the ways that make ordinary matter visible. Gravity is the interaction securely established through its cosmic effects. The phrase "for a reason" must therefore be handled at two depths. At the first depth, the reason is operational and well supported. Photons do not reveal the component because no adequate electromagnetic coupling has been detected. At the second depth, the question asks why that coupling is absent, what law or symmetry controls it, and what entity carries the mass. Science has no confirmed answer there. A candidate model may supply one, but until its distinctive signal is observed, the explanation remains conditional. The title is accurate only if it does not slide silently from the first reason into the second. That is the known behavioral reason. It explains why an optical, radio, infrared, or X-ray image does not simply reveal the dark component. Every one of those instruments depends on electromagnetic radiation. A substance that does not exchange such radiation at detectable levels cannot introduce itself through a conventional picture. But this answer stops sooner than the title may seem to promise. Saying dark matter does not interact meaningfully with light does not explain why nature produced such a component. It does not tell us its mass, internal structure, origin, or exact non-gravitational couplings. It does not choose between a particle, a field, a compact population, a hidden sector, or a deeper framework. Behavior and identity are different scientific achievements. We can know how something acts without knowing what it is made of. Gravity responds to mass and energy on large scales, allowing radically different microscopic entities to produce similar halos, lensing, and structure. Cosmic evidence draws the silhouette. Candidate-specific experiments must reveal the face. The distinction appears elsewhere in science whenever effects are measured before their source is fully understood, but dark matter makes it unusually large. The unknown component is not a minor correction. Within LCDM, it dominates the matter inventory and influences structure across cosmic history. Strong knowledge of its abundance can coexist with ignorance of its particle mass. Strong limits on its interaction can coexist with ignorance of whether it is a particle in the familiar sense. This uneven knowledge is not failure. It is the exact shape of the current result. This is not a contradiction. Scientific confidence can occupy layers. The existence of a gravitational phenomenon can be strongly supported. Its description within a successful model can be precise. Its microscopic explanation can remain uncertain. Treating all three as equally known would create false certainty. Treating all three as equally unknown would discard real evidence. The fifth layer is philosophical interpretation. Most matter appears to lie outside direct light-based access. That fact can feel unsettling because vision has always shaped the human idea of reality. Yet the emotional response is not another scientific measurement. Dark matter is not known to be hostile, conscious, approaching, or dangerous. The word terrifying describes a human reaction to the limit, not a property of the component. The real unease comes from the division between influence and access. Dark matter helps shape galaxies and clusters while withholding the electromagnetic signals through which we know ordinary substances. It participates in cosmic history without becoming a normal image. Even carefully designed nuclear recoil searches have not yet supplied a confirmed identity. Still, invisible does not mean unknowable. Motion reveals distribution. Lensing reveals location. The CMB reveals abundance and early behavior. Structure reveals speed and stability constraints. Cluster collisions limit strong self-interaction. Null experiments remove proposed couplings. Each method turns an absence of ordinary light into positive information. This is the central reversal of the documentary. At first, darkness appeared to mark the place where knowledge stopped. The investigation shows that darkness can become a controlled condition. If no light comes from the component, scientists use objects that move through its gravity. If motion leaves ambiguity, they use bent background light. If mature structures are complicated, they use primordial radiation. If cosmic evidence cannot identify the particle, they build detectors for candidate-specific interactions. Each limitation generates another test. The result is not complete access, but it is a disciplined expansion beyond sight. The result is a measured boundary rather than a blank wall. On one side, science knows that visible matter is insufficient within the leading framework. It knows the additional component is mainly non-baryonic, gravitationally active, dark to light, sufficiently cold, long-lived, and mostly collisionless. On the other side, its identity and deeper origin remain open. Every part of the known profile should retain its qualifier. Mainly non-baryonic allows ordinary matter to coexist in the same structures. Dark to light means below detected electromagnetic levels, not a proof of perfect isolation. Sufficiently cold refers to structure growth rather than touch. Long-lived means stable enough across the observed history. Mostly collisionless allows weak self-interaction. These qualifiers are not evasions. They show exactly where evidence ends and candidate freedom begins. Removing them would make the conclusion sound cleaner, but less true. This boundary could move. A reproducible laboratory signal might identify a particle or field. A gravitational observation might reveal a characteristic compact population. A more successful theory of gravity could reorganize part of the evidence. Science does not protect the current silhouette from correction. It defines what a replacement must explain. Any replacement must preserve the full convergence. It must account for galaxy dynamics, cluster mass, lensing separation, baryon limits, CMB structure, and the growth of the web. Solving one scale while losing the others would not be a deeper explanation. The burden is large because the evidence is distributed across independent eras and methods. So what remains unknown is not whether anything has been measured. What remains unknown is the ontology beneath those measurements, the physical kind of thing whose gravity we infer. We do not know why its electromagnetic coupling is absent or so weak. We do not know whether one component supplies all the dark matter or several share the role. We do not know whether our current candidate categories contain the answer. Nor do we know whether future discovery will make the present picture seem simple or incomplete. A particle detection could connect laboratory physics with cosmic halos. A field signature could require a less familiar description of matter. A compact object population might supply only one fraction of the total. A revised theory of gravity could preserve an unseen component while changing how its distribution is inferred. These possibilities have unequal support, but none can be promoted to fact before evidence distinguishes it. The correct boundary is therefore active rather than passive. It tells researchers which measurements would move a claim from speculation to inference, and from inference toward identification. It also prevents the title's emotional promise from becoming misinformation. The reason dark matter avoids light is constrained at the level of interaction. The reason nature contains that interaction pattern is still a question. The scientific climax is therefore a double conclusion. The universe behaves with remarkable consistency, as though most matter is invisible to light and different from ordinary baryons. Yet the deeper reason for that invisibility remains undiscovered because the entity responsible has not been identified. Both halves must remain together. Emphasizing only the first creates false confidence that dark matter is fully understood. Emphasizing only the second creates false doubt that dark matter is merely an unsupported invention. The accurate position is stronger and stranger. Science possesses a coherent, quantitative account of what the component does across enormous scales, while lacking the microscopic fact that would ordinarily make a substance feel familiar. Its gravitational biography is detailed. Its physical identity card is blank. Dark matter is invisible for a measured reason. It does not measurably communicate through light. It remains mysterious for a deeper reason. Science does not yet know what it is. In 2 sentences, that is the title's complete scientific answer. The first sentence belongs to constrained behavior supported by cosmic observation and experimental limits. The second marks the unresolved identity problem. No evidence currently turns the unknown cause into a threat. No uncertainty about identity reduces every gravitational result to guesswork. The answer is powerful precisely because it refuses to exchange accuracy for either drama or comfort. That answer removes the false menace without removing the wonder. The component is not terrifying because evidence reveals a hidden threat. It is unsettling because the majority of matter can be physically consequential while remaining outside the channel that made the visible universe familiar. Calling this epistemic does not make it abstract. The limit affects real measurements and experimental choices. Telescopes cannot simply collect more of a signal that the component does not provide. Detectors must wait for interactions so rare that backgrounds become central scientific objects. Cosmology must infer abundance through patterns rather than samples. The unease comes from recognizing that reality need not present itself through the forms of access humans find intuitive. The achievement comes from proving that intuition is not the final boundary. That boundary is where the scientific answer ends and the human reflection can begin. The final question is therefore human rather than technical. If darkness is not absence, and if sight is not the limit of evidence, what does this investigation reveal about the reach of knowledge itself? Return to the spiral galaxy, where this investigation began. Its center still shines. Its arms still curve outward through the night. The bright disk still appears to fade into an empty border where fewer stars mark the shape. Nothing in the image itself has changed. What has changed is what the darkness now means. At first, the fading light seemed to mark the end of the galaxy. The visible material grew sparse, so the surrounding region appeared almost empty. But outer stars and gas continued moving under a gravitational influence that the luminous disk could not supply. The edge of the picture was not the edge of the physical system. Gravity extended the galaxy beyond its light. Lensing showed that unseen mass could be mapped without receiving photons from it. The oldest radiation revealed that ordinary matter could not fill the cosmic inventory. The growth of the web showed an invisible component guiding where luminous structure later gathered. None of this has produced a normal portrait of dark matter. No particle has been confirmed as the substance filling the halo. No candidate has earned the right to replace the silhouette with a face. The identity remains unknown, and a final reflection should not pretend otherwise. Yet unknown identity does not return the dark outskirts to emptiness. Their influence is measured. Their required mass is constrained. Their connection with structures across cosmic time is tested through several independent methods. The region is not scientifically blank merely because it refuses to shine. Human vision samples a narrow form of access. Our eyes respond to a small part of the electromagnetic spectrum. Telescopes expand that range, collecting radio waves, infrared light, ultraviolet radiation, X-rays, and gamma rays. But every one of those signals still belongs to the same broad messenger: electromagnetic radiation. Dark matter exposes the limits of that messenger. A larger telescope cannot collect photons that a substance does not provide. More sensitive cameras cannot photograph an interaction that does not occur at a measurable level. Reality is not required to communicate through the channel human senses find most natural. That limit could be treated as defeat. Instead, it became a method. Scientists measured motion when light could not supply enough mass. They used distant light when the hidden component produced none of its own. They examined primordial patterns when mature galaxies became complicated. They built quiet detectors when gravity could describe behavior but not identity. Each method reached beyond direct sight by asking a narrower question. What changed? Where did the light bend? How quickly did the structure grow? Which predicted recoil failed to appear? Knowledge advanced through consequences rather than possession. This is not unlimited power. Inference can be wrong. Models carry assumptions. Instruments contain backgrounds. Several identities can produce similar gravitational effects. The boundary established by the evidence must remain visible. Dark matter's behavior is constrained more strongly than its nature. Humility begins there. The universe contains more than the part that introduces itself easily. Familiar matter forms every eye, telescope, mirror, and detector humans have built. Yet familiar matter appears to be the minority of the total matter inventory. Our direct experience is not a representative sample of cosmic reality. But humility is not helplessness. Human knowledge has never depended on touching every object or seeing every cause directly. It grows by finding stable relationships, testing alternatives, and allowing different measurements to challenge one another. An invisible cause becomes scientifically real, not through imagination, but through the consistency of what it makes the visible universe do. The unsettling part of dark matter is therefore not a hidden threat. It is the recognition that physical importance and sensory access are not the same. Something can shape galaxies, clusters, and cosmic history while remaining absent from every ordinary photograph. Something can dominate the matter inventory without becoming familiar. The reassuring part, if one exists, is equally restrained. The absence of direct light did not end the investigation. It forced sharper questions. Darkness became a measurable condition. Uncertainty became structured rather than empty. Every failed candidate test narrowed the possible answer without erasing the phenomenon that required one. We should not turn that achievement into certainty the evidence has not earned. The underlying entity may surprise us. Present categories may prove incomplete. A future explanation may alter parts of the silhouette while preserving the observations that drew it. The honest ending leaves that possibility open. Look once more at the galaxy's faint outer boundary. The stars there are not simply disappearing into nothing. Their motion carries information from a wider gravitational system. The surrounding darkness is not a painted background. It participates in the galaxy's structure even when it contributes no visible glow. The opening image has therefore reversed its meaning. Light no longer defines everything present. It defines what one messenger can reveal. The dark region no longer marks the place where reality ends. It marks the place where direct vision gives way to evidence. That is what dark matter has taught us. Before revealing what it is, the universe can remain hidden without remaining silent. Gravity can speak where light does not. Patterns can disclose what no image contains. Human perception may be narrow, but careful reasoning can reach beyond it. This does not close the scientific mystery. It changes our relationship to it. The unknown is no longer an invitation to place any story inside the dark. It is a defined space bordered by measurements, failed alternatives, surviving possibilities, and questions precise enough for future evidence to answer. We know why ordinary light does not reveal the component at detected levels. We do not know the deeper origin of that silence. Holding both truths together is more honest than pretending the universe is fully visible or completely beyond understanding. And in that changed view, darkness becomes not a failure of knowledge, but the boundary that taught knowledge how to grow beyond human sight. The galaxy still fades into darkness. We simply no longer mistake the darkness for absence.